Welcome to Stellar Sleep Tales. This is your moment to unwind, to breathe deeply, and to let your thoughts gently drift as the day winds down. Tonight, we're heading back, way back, to a time when Earth looked nothing like the peaceful blue planet we know today. Before there were oceans, forests, or continents, our planet was a fiery, chaotic world. The surface bubbled with molten rock, the air was thick with toxic fumes, and the sky glowed red under a young, volatile sun. It was a planet of lava, and somehow, from that intense beginning, everything we now call home began to take shape. Before we dive in, I'd love to know, where are you listening from tonight? Maybe you're tucked into bed in a quiet city apartment, or lying back in the countryside where the stars still shine bright. If you enjoy these calming journeys through science and wonder, please consider liking the video and subscribing. It truly helps more than you might think. And to those already subscribed, thank you. Your support keeps these stories alive. As always, I hope this video helps you drift off peacefully, but if it happens to keep you awake, at least you'll be learning something fascinating about Earth's fiery past. So let's begin. Try to imagine Earth not as the blue marble we see from space, but as a glowing ball of liquid rock, a place where the ground flowed like lava and the sky was filled with smoke. What would it feel like to stand on such a planet? And how did this blazing start eventually lead to oceans, skies, and life? The Earth we know today, with its water, land, and life, was born from fire. To understand how that happened, we need to travel back more than 4 billion years to a time when the solar system was still forming. Back then, the sky wasn't just filled with stars. It was crowded with debris, planetesimals, asteroids, and stray comets, all swirling around a newborn sun. These leftover pieces from the solar system's construction were constantly crashing into each other, merging, and reshaping into the first planets. Earth was one of the survivors, but survival meant being hit again and again by fiery bodies, each impact unleashing incredible heat. With every collision, the planet grew larger and hotter. Eventually, the surface melted into a global ocean of lava, a constantly shifting sea of molten stone. There was no solid ground, no continents, and no oceans. Just liquid rock, changing shape moment by moment. Above it, the atmosphere was thick with vaporized minerals and gases, sulfur, carbon dioxide, water vapor, and methane, painting the sky in shades of red and gray. The sun, dimmer than it is today, was hidden behind clouds of smoke, casting a strange glow over the boiling world below. And yet, in the middle of all this chaos, the building blocks of our future were forming. Minerals began to take shape, the chemical ingredients for oceans, and eventually life, were already present. Even the moon was about to arrive, born from a massive collision that changed Earth forever. This is the strange truth at the heart of Earth's story. The same violence that made it a world of fire also paved the way for it to become a world of water, a place where life could begin. To follow this transformation is to understand not just how Earth formed, but why it's so different from its neighbors like Venus and Mars. In this journey, We'll explore Earth's earliest moments, its fiery collisions, molten seas, and toxic skies, and trace the slow cooling that brought the first rains, the first oceans, and eventually the first sparks of life. We'll compare Earth's path to that of other planets, look at how scientists uncover clues about the ancient world, and reflect on the surprising fact that we're only here because our planet was once an inferno. As you listen, let your thoughts wander. Think of Earth not as a fixed, solid place, but as a living story, one that began in fire and still carries that heat deep within its core. Even now, beneath your feet, the center of the planet glows with the same energy that once covered its entire surface. So here's the question: how does a planet survive its own fire? And how did Earth turn a sea of lava into the seas of life? In the beginning, before there was Earth, before there were oceans or mountains, there was only a cloud. Not the kind you see in the sky, but a vast cosmic mist stretching across light years of space. It was cold, quiet, and made from the scattered remains of ancient stars that had died long before the sun was born. Inside this cloud were the raw materials of everything: hydrogen and helium from the Big Bang, and heavier elements like carbon, oxygen, silicon, and iron, created in the explosive deaths of older stars. Astronomers call this cloud the solar nebula, a swirling, slowly collapsing mass that would eventually give rise to the sun and the planets. It might not sound like much, just dust floating in the dark, but this dust was remarkable. Each tiny grain held the memory of cosmic history. Some came from supernova explosions. Others formed in the winds of red giant stars. All of them drifted silently, waiting like seeds in the night. The solar nebula wasn't still. Gravity, the quiet force that shapes the universe, began to pull it inward. What was once a peaceful cloud started to collapse. As it did, it began to spin faster, like a figure skater pulling in their arms. A flat, spinning disk formed, with most of the mass gathering at the center. That central bulge would become the sun, still in the process of forming, while the outer parts of the disk held the leftover material that would eventually become planets. Picture it: a giant disk of gas and dust stretching billions of kilometers, glowing softly as heat built up from friction and collapse. At the center, the sun hadn't ignited yet, but pressure was building. When it finally did, it would shine with light and energy, sweeping through the disk and changing everything around it. But before that moment, the edges of the disk were a workshop of creation. Tiny particles of dust bumped into each other and stuck together. At first, they formed small clumps, no bigger than grains of sand. But as collisions continued, they grew stronger. Over thousands, then millions of years, they became pebbles, then boulders, and eventually planetesimals, mountain-sized bodies drifting like silent ships through the young solar system. Their gravity pulled in more material, and when they collided, they released huge amounts of heat. It was a messy, violent process, but it's how planets are born. Not all the material became planets. Some stayed behind as asteroids, comets, and meteoroids, wandering leftovers from that early construction. But within this swirling mix, Earth was beginning to form. The elements that make up the ground beneath your feet, the oxygen you breathe, and even the calcium in your bones were already present, floating in that nebula, waiting to come together. The recipe for Earth wasn't random. Depending on how far a substance was from the sun, it could either survive or burn away. Close to the sun, where it was hot, only metals and rocky minerals could last. That's why the inner planets, Mercury, Venus, Earth, and Mars, are all rocky worlds. Farther out, beyond what scientists call the frost line, it was cold enough for gases and ices to remain. That's where the gas giants, Jupiter and Saturn, and the icy planets, Uranus and Neptune, took shape. Earth's location was just right for a rocky planet with the potential to hold liquid water. And the dust in the nebula wasn't just plain particles. Some carried carbon-rich compounds, including simple organic molecules. Others held tiny bits of water ice. These specks were the building blocks of chemistry, the first hints that someday life could emerge. It's humbling to realize that long before oceans rolled or forests grew, the ingredients for life were already floating silently in space, waiting. When the sun finally ignited, its light and solar winds swept through the disk. Much of the lighter gas was blown outward, especially near the center, but the heavier dust and rock stayed behind. These survivors kept clumping together, their collisions forming larger and larger bodies. The early solar system was a dangerous place, full of impacts and heat, but every crash was a step toward creation. Over time, through countless collisions and reshuffling, the scattered planetesimals orbiting the early Earth began to merge into one dominant body. That growing mass kept getting hit by other large objects, each impact adding more material and heating its surface until it was completely molten. Even in its earliest, most chaotic phase, the forming Earth was already shaped by the elements it had gathered from the solar nebula. Think about what that means. The iron deep in Earth's core was created in the hearts of stars that died long ago. The silicon that makes up much of Earth's crust was born in stellar furnaces. And the oxygen we breathe started out as free-floating atoms in space, which later condensed into grains and became part of minerals. When you look at Earth, you're literally seeing stardust, recycled, compressed, and transformed into a planet. Eventually, the solar nebula faded away, swept clean by the sun's radiation and solar winds. What remained were the planets, moons, asteroids, and comets we know today. But back then, that nebula was a nursery, a place where worlds were just beginning to form. To picture it is to imagine a cloud that was never meant to stay a cloud. It was destined to become something more, stars burning brightly, planets circling them, and stories waiting to unfold. It's easy to think of Earth as solid and unchanging, but its origins lie in something fragile, a drifting cloud of dust and gas, as delicate as smoke, yet powerful enough to spark stars and build entire worlds. From that quiet beginning, the stage was set for a planet that would one day hold oceans, forests, and perhaps most remarkable of all, listeners like you. So before Earth was a ball of fire or a home to seas, it was just a cloud of dust in the dark, a cloud that carried the promise of a world. That dust didn't stay dust for long. Gravity, always patient, began pulling clumps of matter together. What started as tiny grains of stardust grew into pebbles, then boulders, and eventually massive planetesimals, proto-worlds large enough to tug at each other with their own gravity. These wandering bodies orbited the young sun like a crowded dance floor, each crossing path ending in a collision that reshaped them. But this wasn't a graceful process. Imagine millions of rocky fragments flying through space at incredible speeds, smashing into each other with the force of countless nuclear explosions. When two planetesimals collided, the impact melted rock, vaporized minerals, and flung molten debris into space. Some of that debris fell back to the growing bodies, making them larger and stronger. Other fragments were lost forever, scattered across the void. This was the environment where Earth began to take shape. Over millions of years, these collisions built bigger and bigger bodies. Smaller ones were shattered, while the larger survivors absorbed their neighbors. Slowly, a few dominant worlds emerged from the chaos. One of them was steadily gaining mass, the proto-Earth. Each impact made it grow. Each collision heated it until its surface glowed. It's no exaggeration to say that Earth was forged in fire, a planet born from relentless cosmic bombardment. If you're picturing this as a graceful ballet, it's time to adjust that image. Accretion wasn't elegant. It was more like a cosmic demolition derby. Rocks and molten debris slammed together from every direction. Astronomers sometimes compare it to a snowball fight, but that doesn't quite capture the drama. It was more like a snowball fight, where every snowball explodes on impact, melts into lava, and sticks to whatever it hits. Messy, chaotic, and surprisingly effective at building planets. With each new collision, the proto-Earth grew heavier. Its gravity became stronger, pulling in even more wandering planetesimals. The bigger it got, the more it attracted, and the more it attracted, the bigger it became. It was a runaway cycle of growth, turning scattered debris into a full-fledged world. The energy released during these impacts was staggering. Every collision turned motion into heat. With so many high-speed impacts, the surface of the young Earth became a vast ocean of molten rock. The crust melted completely, glowing like a giant ember in the darkness of space. Scientists call this state a magma ocean, a world where there was no difference between land and lava. If you could stand near it, which you couldn't, you'd see a horizon of fire stretching in every direction. As Earth grew, its interior began to organize itself into layers. Heavier elements like iron and nickel sank toward the center, forming the core. Lighter silicate materials floated upward to create the mantle and crust. This process, known as differentiation, laid the foundation for Earth's structure. It also released even more heat as dense materials moved and settled. Between the constant bombardments, radioactive decay, and the formation of the core, the young Earth stayed in a near-permanent state of molten upheaval. While this fiery beginning sounds harsh, it was absolutely necessary. Without these collisions, Earth wouldn't have grown large enough to hold onto an atmosphere or support liquid water later on. The impacts that melted the surface also mixed the planet's ingredients, spreading metals, minerals, and volatile compounds throughout. In a way, the violence of accretion was a kind of cosmic preparation, shaping a planet ready for more complex stories in the future. Even as Earth became stronger, the collisions didn't stop. Some were so massive they nearly tore the planet apart. One day, a Mars sized body named Theia is believed to have slammed into Earth, blasting molten rock into orbit and forming the moon. That story deserves its own spotlight, but it shows just how intense this era was. Earth's growth wasn't a gentle gathering of dust. It was a series of colossal impacts, visible across the newborn solar system. The violence of this time is hard to imagine. Each impact released more energy than the asteroid strike that wiped out the dinosaurs billions of years later. But back then, these impacts weren't rare. They were constant. The surface never had time to cool before being hit again, reheating the crust, reshaping the terrain, and keeping the planet in a molten state. Meanwhile, the sun was maturing, burning brighter and sending out streams of charged particles. These solar winds swept across the disk, stripping away much of the lighter gases from the inner solar system. What remained were the heavier materials that would form the rocky planets. So Earth's fiery formation wasn't just about collisions, it was also about surviving the sun's early storms. The story of Earth's accretion is full of contradictions. It was a destructive process, but it created something new. Each impact erased what came before, but the fragments came together to form something larger, something lasting. The Earth you know today, with its mountains, oceans, and fields, was born from countless acts of destruction. Each impact was a small ending that contributed to a much greater beginning. It's worth pausing to imagine what this would have looked like to an observer from afar. Picture yourself standing on a nearby planetesimal, watching the proto-Earth glowing in the distance. You'd see a sphere wrapped in fire, with impacts flashing like sparks as new material rained down. Each strike would send molten rock splashing into space, arcs of glowing liquid stone tracing across the darkness. It would have been a sight both terrifying and inspiring, a raw vision of creation in motion. As the number of wandering planetesimals dwindled, Earth's rapid growth began to slow. The most intense phase of accretion eventually ended, leaving behind a planet larger, hotter, and more complex than before. Bombardments would continue for millions of years, but the foundations of a world were now in place. Earth was no longer a drifting cloud of dust or a loose scattering of rocks. It had become a single, growing body with its own destiny. From dust to planetesimals, from planetesimals to a molten sphere, its path was shaped by fire. The relentless impacts that once threatened to destroy it only made it stronger. It's easy to think of Earth as solid and safe, but its origins tell a different story, one built on chaos. The ground beneath your feet was forged in collisions so violent they melted rock. And yet, from that violent beginning rose the stable world that now supports oceans, forests, and life. The accretion of Earth was a cosmic construction project unlike anything else, built not with tools or blueprints, but with gravity, chaos, and fire. It was loud, brutal, and unending, and yet, in the aftermath, a planet emerged, a world destined to transform from fire to water, from molten chaos to the cradle of life. Now, imagine standing on the surface of the early Earth, if such a thing were even possible. There would be no solid ground beneath you. Instead, you'd be surrounded by an endless, heaving expanse of molten rock stretching in every direction, an ocean of fire. Waves of glowing orange and red magma would rise and fall, currents of molten stone swirling and colliding. The horizon would shimmer with heat, and the air would be thick with smoke, gases, and the glow of a world not yet cooled into stability. Scientists call this stage the magma ocean, and it's one of the most extraordinary chapters in Earth's history. The young planet had been battered by so many collisions that each new impact melted the crust again and again. Eventually, the strikes became so frequent and so powerful that the entire surface was reduced to a global sea of lava. This wasn't a world of scattered volcanoes or isolated lava flows. The whole Earth was a volcano. Its outer shell was nothing but molten rock in constant motion. To picture it, think of modern volcanic scenes, the glowing rivers of lava flowing from Kilauea in Hawaii, or the fountains of molten rock erupting in Iceland. Now, expand those scenes until they cover the entire planet. There were no safe islands, no cool patches of rock, only a restless surface where temperatures soared well above 1,000 degrees. From space, Earth wouldn't have been the familiar blue marble, but a glowing sphere pulsing with the light of liquid rock. Colors would shift from deep reds to bright yellows, with darker crusts forming briefly before sinking back beneath the molten waves. The atmosphere, thick with volcanic gases and vaporized rock, would blur the view, wrapping the planet in a hazy shroud that glowed with reflected fire. And the sound? A magma ocean would have been anything but quiet. The molten surface would bubble, roar, and crack as currents shifted and gases escaped. Imagine the hiss and pop of lava meeting seawater today, but magnified to cover the entire globe. Explosive eruptions would break through the constant low roar as bubbles of gas burst from beneath the surface and hurled fountains of magma skyward. The noise would have been deafening, a thunderous symphony of fire and stone echoing across the newborn world. And the feeling? The heat would have been unbearable, radiating outward in waves so intense that any solid object nearby would melt or vaporize. The air, if it could even be called that, was thick with choking gases, carbon dioxide, sulfur dioxide, methane, and water vapor. It was dense, poisonous, and utterly hostile to any form of life we know.
The pressure from steam and ash created a heavy, suffocating sky, dark, yet faintly glowing with the reflection of firelight from below. The ground, if you could touch it, would yield like liquid, shifting and flowing beneath you. This was not a stable home, it was a cauldron of creation. And yet, scientists aren't guessing blindly about this alien scene. The evidence comes from both geology and physics. Earth's layered structure, its iron core, silicate mantle, and rocky crust, shows that the entire planet must once have been molten, allowing heavier materials to sink and lighter ones to rise. Computer models of planetary formation confirm that the energy from constant collisions, combined with radioactive heating and gravitational compression, would have been more than enough to keep the surface liquid for millions of years. Even the Moon holds clues. Rocks brought back by Apollo astronauts reveal that it, too, once had a magma ocean. The Moon cooled faster than Earth because of its smaller size, but the similarity suggests this molten stage was common for young rocky worlds. Many planets and moons likely began as seas of liquid rock before becoming the solid bodies we see today. To grasp the scale, it helps to compare it to modern volcanoes. Today, lava flows from an eruption can travel for kilometers, reshaping the land as they cool. But those flows are tiny compared to a planet-wide magma ocean. The lava lake at Kilauea's summit, spectacular as it is, would be like a single drop in the fiery sea that once covered Earth. Even the largest eruptions in human history, such as the massive lava flows that formed the Deccan Traps in India, pale in comparison. It was as if every volcano that has ever erupted was active at the same time, their flows merging into one global ocean of fire. One striking feature of the magma ocean would have been the temporary formation of crust. As the surface radiated heat into space, thin skins of solid rock would sometimes form, darkening against the glowing magma. But these crusts were fragile, quickly broken apart by currents below or shattered by new impacts from space. Chunks of crust would sink back into the molten depths, recycled again and again. Earth was trying to cool, but the process was constantly interrupted, trapping it in a fiery balance between heat and escape. It's tempting to see the magma ocean as pure destruction. But it was also creation. Within its molten depths, elements mixed and separated, forming the layered structure that still defines Earth today. The formation of the core generated a magnetic field that would one day help shield the planet from harmful solar radiation. Outgassing from the molten mantle created the first atmosphere, laying the groundwork for the air we breathe. Even in its most violent and unstable state, the magma ocean was shaping the conditions for the planet's future. From afar, the young Earth would have been breathtaking, a glowing sphere wrapped in a halo of smoke and gas, pulsing with energy. It would have looked alive, even before life began. The contrast between the cold emptiness of space and the fiery turbulence of Earth would have been unforgettable. Eventually, the magma ocean began to cool, a process that took millions of years. But in this stage, Earth was at its most dramatic, a world defined by molten chaos. Though no eyes were there to witness it, the echoes of that fiery past remain locked in the rocks beneath our feet and in the restless rumblings of volcanoes that still break through the surface today. The magma ocean was not a gentle beginning. It was hot, loud, and utterly hostile to life as we know it. Yet within its molten heart lay the seeds of stability, the first steps toward cooling, toward oceans, toward landscapes that would one day define the Earth. It looked like chaos, but it was in truth the earliest stage of order, shaping the planet into the home we know now. More than 4 billion years ago, Earth was already a fiery, restless place. But its most dramatic moment was still to come. Among the countless collisions that shaped the young planet, one stands out as the most cataclysmic of all. Astronomers call it the Giant Impact, and from its chaos came one of Earth's most enduring companions, the Moon. The story begins with a wanderer. In the crowded early solar system, the region around Earth was filled with large planetesimals, each on its own unpredictable path around the Sun. One of these bodies, roughly the size of Mars, crossed paths with the growing Earth. Scientists have named this ancient world Theia. Its orbit was unstable, and gravity eventually drew it inward until a collision became inevitable. What followed was not just another impact, it was one of the most extraordinary events in planetary history. When Theia struck Earth, the energy released was beyond anything we can truly imagine. This was no asteroid strike, it was a head-on collision between two planets. The impact melted vast regions of both worlds, blasting molten rock and vaporized material high into space. Entire chunks of Earth's mantle were hurled into orbit, forming a glowing halo of debris. Earth's molten ocean was stirred like a cauldron in an instant. From this chaos, the moon began to take shape. The debris in orbit didn't remain scattered for long. Gravity, the quiet architect, pulled the fragments together. In perhaps only months or years, they coalesced into a single body. The newborn moon was hot, glowing, and much closer to Earth than it is today. In those first moments, it would have loomed huge in the sky, a fiery orb above a fiery planet. Evidence for this story comes from the rocks themselves. Lunar samples brought back by Apollo astronauts have isotopic fingerprints nearly identical to Earth's mantle, suggesting the moon formed from the same material. This fits perfectly with the giant impact hypothesis. The moon is, in a sense, a piece of Earth, reshaped into a separate world by a violent encounter. The moon's early appearance would have been extraordinary. Newly formed, it too was covered in a magma ocean, glowing like a lantern above the molten Earth. Over time, it cooled and solidified, leaving behind the craters and basins we still see today. The moon we know now, with its quiet gray surface, is the calm descendant of that fiery birth. And its arrival did far more than give Earth a companion in the night sky. It profoundly altered the planet's future. One of the moon's most important roles has been keeping Earth's rotation steady. Without it, our planet's axis could have wobbled wildly over time, tilting one way, then another, under the combined gravitational pull of the Sun and other planets. Such instability would have caused extreme climate swings, making it far harder for life to take hold. The moon's constant gravitational pull acts like an anchor, holding Earth's tilt within a relatively narrow range. This stability has lasted for billions of years, giving life the calm, predictable conditions it needed to slowly evolve. The moon also gave us tides. Its pull on Earth's oceans creates the rhythmic rise and fall of water across the globe. In the distant past, when the moon was much closer, tides were far stronger, reshaping coastlines and stirring the chemistry of shallow seas. Many scientists believe these powerful tides may have helped spark the early evolution of life, cycling nutrients and energy in ways that encouraged complexity. Another gift from the moon is its effect on Earth's rotation. When it first formed, the moon orbited much nearer to Earth, and our planet spun far faster, completing a day in just a few hours. Over time, the gravitational interaction between the two slowed Earth's spin, stretching days to the 24-hour rhythm we live by now. At the same time, the moon has been slowly drifting away, still receding today at a rate of a few centimeters per year. In the far future, Earth and the moon will become tidally locked, each always showing the same face to the other. It's remarkable to think how much of our world is shaped by that ancient collision. The beauty of a full moon rising, the predictability of tides, the stability of our seasons, all trace back to that single, fiery encounter more than 4 billion years ago. Had Theia never struck Earth, our planet might be far less stable, less hospitable, and perhaps without the familiar light that has guided human eyes and imaginations for millennia. Even today, traces of that impact may remain deep within Earth. Some geologists believe remnants of Theia still lie buried in the mantle, vast regions of unusual material far below the surface. If so, the moon is not the only reminder of that collision. Earth itself still carries the memory. From destruction came creation. The impact that nearly tore Earth apart instead gave rise to a companion that has shaped our planet ever since. The Moon is more than a silent satellite, it's a fragment of Earth's own body, born in fire, forged in violence, and transformed into a stabilizing presence that has guided our planet's story for billions of years. When you look up at the Moon tonight, you're not just seeing a gray, cratered rock. You're looking at a relic of Earth's fiery youth, a reminder that even the most violent beginnings can lead to enduring beauty. The gentle glow that lights the night sky was once molten debris flung from a planet in chaos. Without it, Earth would be a very different place. The Moon is both scar and gift, a child of fire that became a guardian of stability, and a constant reminder that creation often walks hand in hand with catastrophe. Above the glowing surface of the young Earth, the air offered no refuge. The sky was as restless as the molten world below, thick with fumes and vapors pouring endlessly from the planet's fiery heart. Volcanic eruptions were constant, each one releasing clouds of carbon dioxide, methane, ammonia, sulfur compounds, and ash. This was nothing like the calm blue sky we know today. Instead, it hung heavy and suffocating, a haze of smoke and fire. The early atmosphere was born through a process called outgassing. As the magma ocean churned and volcanoes erupted, gases trapped in molten rock escaped into the air. Steam, carbon dioxide, and sulfur dioxide were among the first to rise, forming a dense shroud around the planet. In those days, the air was not breathable, not even close. It was toxic, heavy, and dense, more like the emissions from 1,000 volcanoes erupting at once in today's world. This thick veil meant the sky was not blue. Blue skies require a relatively clear atmosphere where sunlight scatters off nitrogen and oxygen molecules. But on the young Earth, sunlight had to pass through a soup of dust, vapor, and greenhouse gases. The result was a sky glowing with rusty reds, hazy oranges, and dim grays. At times, the planet may have seemed locked in twilight, even at midday, with only a weak glow from the sun filtering through the haze. The greenhouse gases in this sky played a crucial role. Carbon dioxide and methane trapped heat, keeping the surface hot even as Earth radiated energy into space. Without them, the planet might have cooled much faster. Instead, they acted like a thermal blanket, holding in warmth and keeping Earth molten for millions of years longer. Sulfur gases added their own dramatic touch. Sulfur dioxide can form aerosols, tiny reflective particles that scatter light. Today, we see this effect in volcanic eruptions that turn sunsets deep red and purple. On early Earth, the effect would have been magnified many times over. Every horizon would have glowed with surreal colors, as if the planet lived under a permanent volcanic sunset, breathtakingly beautiful, yet utterly hostile. Imagine standing at the edge of a molten plain, looking upward. The sun would appear dim, a muted disk behind veils of smoke. Around it, the sky would shift from orange to crimson, fading into purples and grays near the horizon. Ash and aerosols would scatter light into dramatic patterns, while lightning, triggered by the churning atmosphere, forked across the sky. Such lightning storms were likely frequent. Volcanic plumes carry immense electrical charge, and with so much activity, the skies above early Earth would have been alive with flashes of light. Each bolt would have split the haze, illuminating the landscape in blinding bursts. Thunder would have rolled endlessly, blending with the constant roar of erupting volcanoes. The air itself was a stage for ceaseless drama. And yet, this sky was also a chemical laboratory. The gases swirling overhead were the raw materials for the planet's future. Carbon dioxide would one day feed plants and drive the carbon cycle. Water vapor would condense into the rains that filled the oceans. Even methane and ammonia may have played a role in the chemistry that seeded the first living systems. What looked like a toxic wasteland was, in truth, a planetary cauldron brewing the conditions for life. Comparisons to our neighbors are telling. Venus, with its thick carbon dioxide atmosphere, offers a glimpse of what Earth might have become had conditions not shifted, its skies still filled with haze and sulfur clouds, its surface locked in an inferno. Mars, by contrast, lost most of its early atmosphere, leaving behind a thin, cold sky. Earth's path lay between these extremes, a balance that eventually gave rise to breathable air. But in its earliest days, our skies were far closer to Venus than to anything we'd call inviting. The heavy blanket of gases also meant that stars would rarely have been visible from the surface. Unlike today's night sky, filled with countless points of light, early Earth's nights may have glowed faintly red, the haze reflecting the fire below. The moon, if visible at all, would have appeared as a ghostly lantern, blurred and distorted by the dense atmosphere. And among the most striking sights of all would have been the sunsets. Today, the scattering of sunlight gives us golden evenings and fiery twilights. But on the early Earth, the thick haze of dust and gases would have stretched those colors across the entire sky. The whole dome above may have glowed in deep crimson, fading into purple shadows, so intense that our most vivid modern sunsets would seem pale by comparison. Standing on that world, you would have seen skies that looked more like vast, shifting paintings than reality, murals of smoke and fire in constant motion. And while these skies were toxic and dangerous, they were essential to Earth's evolution. They trapped heat, shielded the surface from some of the sun's harshest rays, and kept volatile chemicals close enough to interact with oceans and rocks. In effect, they formed a restless middle ground between the fiery Earth below and the cold vacuum above, a turbulent buffer where chemistry was quietly shaping the planet's destiny. Over time, these gases would transform. Water vapor would condense into rain. Carbon dioxide would be locked away in rocks and, later, in living organisms. Oxygen would eventually rise to fill the sky. But long before that, Earth was a planet of smoke and fire. To look up was to see the atmosphere alive, glowing with color, streaked with lightning, and filled with the breath of a world still learning to be a planet. The skies of early Earth remind us that beauty and danger often walk side by side. They were deadly to breathe, oppressive to stand under, and yet they carried the seeds of everything to come. Beneath their crimson haze, the molten planet waited for its chance to cool. Above, the air churned and glowed, an ever-changing canvas painted by fire. Every horizon burned. Every sunset stretched across the sky. The air itself whispered of transformation. When we picture Earth today, it's easy to imagine continents as immovable fixtures, vast slabs of land anchored in place as if they had always been there. But in the planet's earliest days, there were no continents, no familiar landscapes, and no stable ground at all. Earth was not a world of land and sea, it was a world of fire, its surface an ever-shifting ocean of molten rock. It might seem strange that continents didn't appear right away. After all, the planet was full of rock and minerals, and gravity was already pulling matter together. But the problem was heat, an overwhelming amount of it. The colossal collisions that built Earth released unimaginable energy, melting nearly everything. Radioactive elements in the mantle added more heat as they decayed. And the constant rain of asteroids and comets crashing into the surface kept the temperature high. Any attempt at forming a crust was short-lived. As molten rock spread across the globe, the surface radiated energy into space, creating thin, brittle layers of cooling rock. But these crusts were fragile. They cracked, sank, or were melted anew by the lava ocean below. It was like trying to form ice on boiling soup, a thin film might appear, but it would quickly break apart and vanish back into the heat. If you could hover above this molten world, you'd see plates of dark, solidified rock drifting across fiery seas, only to fracture, sink, or be swallowed again. The surface would have looked like a colossal cauldron, with hardened fragments floating like croutons in an endless stew of magma. None of them lasted. Even the largest slabs were constantly recycled, dragged downward by the restless currents of the molten mantle. The difficulty of forming crust lay in Earth's internal structure. As the planet differentiated, heavy elements like iron and nickel sank into the core, while lighter silicate materials floated toward the surface. This created a mantle in constant motion, heated from below, cooled from above. Hot materials surged upward, cooler materials sank downward, and the surface was caught in the middle of this relentless convection. Imagine a pot of porridge bubbling on the stove. The surface rises, cracks, and falls, never still, always reshaping. That was Earth's face in its earliest era. Modern volcanoes give us a small glimpse of this instability. When lava cools, it often forms a thin crust on top. If you've seen footage of lava creeping across the ground in Hawaii, you'll notice the surface darkens quickly, but the glowing magma beneath pushes through, cracking it again and again. On the young Earth, this happened not locally, but globally. Adding to the challenge was the constant bombardment from space. The early solar system was full of leftover debris, asteroids, comets, and planetesimals still wandering the sun's orbit. Earth was struck again and again. Each impact reheated the crust, shattering any fragile stability. Some collisions were so large they vaporized entire regions of the surface, turning solid rock back into liquid fire in moments. In this chaotic era, the ground itself could not be trusted to hold still. With no continents, Earth's surface was a uniform world, lacking the features we now associate with planetary landscapes. There were no mountains, valleys, or rivers, only the rolling molten tides of the magma ocean. The only topography came from shifting lava flows, the rise and fall of convection currents, and the scars of impacts. And yet, within this instability, the seeds of future continents were already present. Even as crust fragments melted and reformed, some minerals began to separate. Lighter rocks, rich in silicon and aluminum, were more buoyant than the heavier, iron-rich materials beneath them. Over immense spans of time,
these lighter components would help form true continents. But in the early stages, the heat was simply too great for them to gather and persist. The lack of stable continents also shaped the young Earth's climate and chemistry. With no land to erode, there were no soils, no rivers carrying minerals, no weathering of rocks to draw carbon dioxide out of the atmosphere. Instead, volcanic outgassing dominated, filling the air with carbon dioxide, methane, and sulfur compounds. These gases trapped heat, feeding the cycle of fire that kept the crust unstable. Earth was locked in a feedback loop, its fiery surface sustaining a smoky greenhouse sky, and that sky ensuring the surface stayed molten. Comparisons to other worlds highlight how unique Earth's journey was. Venus may also have had a magma ocean, and today its surface is still dominated by volcanic plains. Its thick carbon dioxide atmosphere likely prevented large-scale continental formation. Mars, by contrast, cooled more quickly due to its smaller size. Though it never developed vast continents like Earth, it reached stability far earlier. Earth's delicate balance between fire and cooling delayed the appearance of continents, but ultimately allowed for a more complex geological story. At this stage, you could say the planet was still deciding what it wanted to be. The ingredients for continents were there, but the heat of youth kept them suppressed. It was a world defined by impermanence, where land could not endure, and the very concept of a continent was still millions of years away. Yet this molten stage was not wasted time. The repeated melting and recycling of crust mixed materials thoroughly, distributing elements across the mantle and crust in ways that would later prove essential for life. This recycling also allowed lighter minerals to slowly accumulate, forming the foundation of the first protocontinents once the planet cooled enough. In this sense, instability was a form of preparation, laying the groundwork for the land masses that would eventually rise. To imagine this world is to let go of the idea of permanence. There was no safe ground, no fixed landmark, no place that stayed the same from one moment to the next. Continents, as we know them, did not exist. Earth was still far too young, too hot, and too restless to offer such stability. Instead, it was a shifting sea of lava, a restless tide of molten rock that refused to hold still. Yet within that fiery chaos lay the first hints of what would come, fragments of crust that briefly floated, lighter minerals beginning to separate, and the endless recycling of molten rock. All of these were steps on the long road toward a planet with land and oceans, mountains and valleys. For now, though, Earth was a world without continents, a place where fire ruled without interruption, and where the very idea of land was still a dream waiting to solidify. Across the young Earth's molten surface, there were no rivers of water carving valleys or winding toward distant seas. Instead, the first rivers were rivers of fire, flowing not with cool, life-giving liquid, but with glowing rock streaming downhill in brilliant currents of red, orange, and gold. These were the veins of a planet still in its infancy, coursing with heat and energy rather than water and life. Lava is rock heated to such extremes that it behaves like a fluid. When it flows, it moves slowly, yet with a power that reshapes everything in its path. On modern Earth, volcanic eruptions give us small glimpses of this behavior, lava spilling from rifts in Iceland, or molten streams creeping across the fields of Hawaii. But the scale of the early Earth's rivers of fire was far greater, vast, unbroken currents of molten rock, shaping a world still waiting for its first drop of rain. These were not small, local flows spilling from isolated volcanoes, they were immense torrents sweeping across a global magma ocean. Imagine yourself suspended in the thick, hazy atmosphere above such a scene. Below, waves of lava stretched endlessly in every direction, a restless, shimmering surface of liquid stone. Instead of valleys, you'd see deep channels carved into the molten crust, where faster-moving currents sliced through slower, cooling layers. The surface glowed in shifting colors, bright, almost white-hot regions marking fresh, searing flows, and darker patches showing areas just beginning to solidify. From a distance, the sight would have resembled the branching veins of a living organism, fiery streams merging, splitting, and spreading across the planet's skin. These molten currents were more than a spectacle, they were the first great sculptors of Earth. Just as rivers of water today carve valleys, deltas, and floodplains, rivers of lava shaped ridges, channels, and vast plains of cooled stone. When lava spread and cooled, it built new crust. When it broke apart, it recycled the surface. The entire landscape was in constant motion, like an artist's canvas that could never be finished. Every flow added new layers, erased old ones, and carried the story of Earth's youth forward. The behavior of these fiery rivers depended on their temperature and chemistry. Hotter, thinner lavas moved quickly, streaming like glowing syrup across the surface. Cooler or thicker lavas crept slowly, their surfaces folding and wrinkling into strange textures. Some cooled into smooth, rope-like patterns, others cracked into jagged shards that looked like broken glass. Today, geologists still see these textures in lava fields around the world, echoes of the same processes that once dominated the entire globe. Where currents collided, dramatic fountains erupted. Pressure from below forced magma upward, spraying it into the air in glowing arcs before raining back down. These fountains added to the planet's constant roar, a crackling, booming soundtrack punctuated by bursts of molten spray. Each explosion reshaped the terrain, scattering fresh material that often melted back into the flow. The rivers of fire were not steady streams. They pulsed, shifted, and branched, sometimes surging forward in great waves, other times slowing to a sluggish crawl. Their paths were dictated by the restless currents of the mantle below. Convection acted like an unseen engine, pushing magma upward in some places and dragging it downward in others. The surface was simply the reflection of this deeper turbulence, its fiery rivers tracing the hidden movements of the planet's interior. The atmosphere above was transformed by every flow. Carbon dioxide, sulfur dioxide, water vapor, and methane poured into the sky, feeding the thick, hazy shroud that cloaked the earth. Lightning storms raged as volcanic plumes charged the air. Ash clouds mingled with smoke, scattering sunlight into eerie hues. From the ground, the horizon would glow not with the blues and greens of today's world, but with deep reds and oranges, like an eternal sunset wrapped around the planet. For all its violence, there was something mesmerizing about this world of fire. Watching the molten currents must have been like staring into a slow-motion ocean of light. Waves of rock rolled and collided, glowing brightest where they were hottest, fading darker as they cooled. From above, the planet would have looked alive, pulsing with glowing veins of magma, shifting like the breath of a great fiery organism. These rivers of fire were also vital to Earth's future. By carrying heat from the interior to the surface, they allowed the planet to cool, slowly, but steadily. Each flow radiated energy into space as light and heat. Without them, Earth might have remained molten far longer. They were the planet's first cooling system, venting the energy trapped during its violent birth. As lava cooled, it left behind layers of basalt and other volcanic rock. Over time, these layers built up, creating the first fragile hints of a solid crust. Though constantly recycled, they marked the beginning of a surface that could one day stabilize. The parallels to modern rivers of water are striking. Just as water carves valleys and carries sediments, lava carved channels and spread minerals. Just as rivers eventually meet the sea, lava flows often pooled into vast molten plains before cooling into wide plateaus. The difference, of course, was that these rivers were far hotter and far more destructive, capable of melting anything in their path. Where water nourishes, lava consumed. Yet both were forces of change, shaping landscapes and guiding the planet's destiny. Even now, Earth carries traces of this fiery past. Modern volcanic eruptions are not new, they are echoes of a time when the entire world was a volcanic field. Every lava flow today is a miniature version of what once defined the globe. The rivers of fire may no longer dominate, but they still flow in certain corners of the world, a reminder that the heat of Earth's infancy still lingers deep within. To picture Earth as a world of molten currents is to see it at its most raw and elemental. No continents, no oceans, no forests or deserts, only rivers of fire weaving across a glowing surface, painting the planet in shifting shades of red and gold. It was harsh, toxic, and unstable, yet also breathtaking, a living canvas of molten light. And though dangerous, it was the necessary beginning, the fiery stage upon which all later chapters of Earth's story would unfold. If you could somehow stand on the surface of the young Earth, eyes closed, listening to the world around you, you would not hear silence. There were no birds in the sky, no rivers trickling through valleys, no leaves rustling in the wind. But there was sound, overwhelming, endless, and thunderous. The most constant was the crackle and roar of molten rock. Imagine the hiss of lava meeting air in Hawaii, or the low rumble of an erupting volcano, then magnify it until it filled the horizon. The magma ocean shifted and churned, its fiery currents colliding, breaking through thin crusts, and pouring in bright cascades that hissed and spat as gases escaped. Every bubble of carbon dioxide or sulfur dioxide bursting from the molten depths added a sharp, cracking note to the planet's endless percussion. Volcanoes were not occasional features, they were the very skin of the earth. Everywhere you looked, plumes of fire and ash erupted skyward. Each explosion carried a deep, booming roar, the kind that rattles through your chest like thunder up close. These eruptions dwarfed anything humans have ever seen. Ash clouds filled the sky with a muffled, growling hiss, while glowing fountains of lava roared like jet engines, hurling molten rock hundreds of meters into the air before it fell back into the sea of fire. And then there were the impacts. The early solar system was still crowded with wandering asteroids and comets. When they struck Earth, the sound would have been beyond comprehension. Imagine the crack of a meteorite hitting solid ground today, then scale it up until the collision melted entire regions of the planet. The thunder from such an impact would have rolled across the globe, reverberating through the molten crust like the beat of a cosmic drum. Each strike was not just a crash, but a detonation, a deafening shockwave tearing through the dense atmosphere and shaking the world. The atmosphere itself added its own voice to this symphony. Thick with gases and ash, it was restless and turbulent. Lightning storms were frequent, sparked by the violent churning of volcanic plumes. Each flash was followed by a booming peal of thunder, amplified by the dense air. Thunder was not a distant rumble, it was a constant, crashing drumbeat echoing above the molten plains. The heavy gases carried sound differently. Low rumbles stretched and lingered, wrapping around the listener like waves of pressure. If you listened closely, you'd hear the delicate crackling of cooling rock, thin crusts snapping and fracturing under strain, their brittle edges breaking with sharp pops. Each time molten currents surged beneath the surface, the crust shattered, sending ripples of sound outward. It would have been like ice breaking on a frozen lake, only hotter, sharper, and far more ominous. And beneath it all was the constant hiss of gases escaping from the mantle, steam, carbon dioxide, sulfur, and methane venting endlessly into the sky. Imagine the sound of 1,000 geysers erupting at once, or the hiss of a massive pressure valve slowly releasing. That was the young Earth's breath, a constant exhalation that filled the air with both sound and poison. Weather, as we know it today, did not yet exist. There were no rains, no rivers, no winds sweeping across continents. But there was still something like weather, storms of ash and gas. Winds whipped through volcanic plumes, scattering particles across the sky with a whispering, rushing noise. Ashfall would have pattered against molten surfaces like rain on a metal roof, each grain sizzling as it touched down. Instead of gentle breezes or the crash of ocean waves, the atmosphere carried the shriek of turbulent winds forcing their way through dense clouds of smoke and fire. Silence was rare. On modern Earth, we can find quiet in deserts, forests, or deep caves. But the early Earth had no such refuge. The molten planet was never still. Sound was as constant as heat and light, a reminder of the energy still trapped inside this young world. The closest thing to silence would have been the low, ever-present hum of the magma ocean itself, a deep bass note that never stopped, as though the entire planet was vibrating with its own heartbeat. To imagine this world fully, combine the sounds of every modern volcano into a single, unending symphony, the hiss of lava cooling in open air, the crackle of rock breaking under strain, the roar of fountains of fire bursting from the ground, the thunder of lightning storms overhead, the ground-shaking boom of asteroid impacts, and above it all, the steady hiss of gases venting skyward. This was the soundtrack of Earth's infancy. For humans, it would have been uninhabitable, deafening, terrifying. Yet in another sense, it was mesmerizing. The chaos had rhythm. Each eruption, each crack, each rumble of thunder was part of the process of shaping the world. To listen to the young Earth was to hear the act of a planet becoming itself. Those sounds have long since faded, but they are not gone entirely. Modern eruptions still echo the roar of that fiery past, the hiss of lava meeting the sea, the crackle of cooling rock, the boom of volcanic thunder. All are whispers of what once filled the entire planet. Earth no longer screams with fire as it once did, but its voice can still be heard, if you know where to listen. The early Earth was not a silent, empty sphere. It was a planet of sound, every note born of fire and impact, every rhythm forged in chaos. To stand there would have been to hear creation itself, a restless, thunderous, crackling world where the music of molten stone never ceased. For a brief moment, it might have seemed as if Earth was beginning to calm. The magma ocean was slowly trying to form crust. Thin plates of rock floated across molten seas, and gases built a dense, smoky atmosphere. But peace never lasted. Above the planet, space was full of danger. Millions of rocky fragments, asteroids and icy comets, still wandered the solar system. And for Earth, they did not remain distant. They fell. Astronomers call this violent period the Late Heavy Bombardment, a time when the solar system rained stone and ice upon the young worlds. Imagine meteors streaking through the sky not once a month, not once a year, but constantly, an endless hail of fire from space. Some were the size of boulders, others the size of mountains. Each struck with unimaginable force, releasing energy to rival the most powerful explosions the planet has ever known. The early solar system was not yet neat and orderly. Planets had only recently carved out their orbits, and many smaller bodies still wandered in chaotic paths. The gravitational pull of the giant planets, especially Jupiter and Saturn, sent countless asteroids and comets hurtling inward. With its growing mass, Earth became a prime target. To an observer, the sky would have looked alive with streaks of light, fiery trails burning across the haze as objects tore into the atmosphere. When they struck, the results were catastrophic. Even a rock only a few kilometers wide carried enough momentum to release more energy than millions of nuclear bombs combined. Each impact shattered the crust, hurled molten rock skyward, and sent shockwaves racing around the globe. For a planet already struggling to cool, every strike reheated the surface, undoing whatever fragile stability had begun to form. Craters overlapped craters, their rims blasted apart by newer impacts before they could cool. Some collisions were so massive they vaporized entire regions of rock, turning solid land into glowing plasma. The air filled with ejecta, molten fragments flung high above the atmosphere before raining back down in fiery showers. From the surface, Earth would have seemed caught in a cosmic firestorm, glowing from both above and below. The moon preserves the scars of this era. With no atmosphere and no plate tectonics to erase its history, its surface remains pocked with craters, a permanent record of the storm of impacts that once raged across the solar system. Every crater on the moon is a reminder that Earth, too, was struck countless times. The difference is that Earth's restless geology has since buried its scars beneath oceans, continents, and shifting crust. Comets played their own role in this bombardment. Unlike rocky asteroids, comets are rich in ice, and when they collided with Earth, they delivered water as well as destruction. Some scientists believe a significant fraction of Earth's water may have arrived this way, carried within icy projectiles from the outer solar system. Each collision was a paradox, catastrophic in the moment, yet essential for creating the oceans that would one day cradle life. It was as if the heavens themselves were throwing both fire and water at Earth, shaping its destiny through contradiction. The bombardment also brought essential chemistry. Many asteroids carried organic molecules, complex carbon compounds forged in the cold depths of space. When these rained down onto the fiery Earth, they seeded the surface with ingredients that would later play a role in life's emergence. The same impacts that scorched the crust and filled the skies with fire were also delivering the seeds of biology. The atmosphere during this era would have been surreal. Every impact lit the sky with blinding fireballs brighter than the sun's shockwaves flattened everything in their path. Dust and ash darkened the skies for weeks or months, plunging the surface into eerie twilight. Then, as debris settled, greenhouse gases from molten rock and vaporized materials trapped heat, bringing intense warmth again. The climate swung violently between searing heat and choking gloom, a cycle dictated not by seasons, but by the rhythm of falling stones. The sound of the bombardment would have been deafening. Each impact cracked the air and shook the ground. The roar of erupting magma mixed with the thunder of atmospheric entry, followed by the bone-shaking boom of collision. For long stretches, Earth was nothing but a cacophony of explosions and crashes, the air trembling with the violence of the skies. Yet the bombardment was temporary. Over time, the number of wandering bodies dwindled. Jupiter and Saturn cleared much of the debris, either swallowing it or flinging it into the outer reaches of space. Earth still absorbed its share, but gradually the rain of fire eased. The planet could finally begin to cool more steadily. Rock crusts survived longer without being shattered anew. But for millions of years, Earth had endured a storm so intense it reshaped everything about its surface and its destiny. Looking back, the late heavy bombardment was both a trial and a gift. It delayed Earth's cooling, keeping it a world of fire longer than it might have been. But it also delivered water, organic molecules, and a rich mix of elements that would become part of soils, seas, and living cells. The firestorm from space was both destroyer and benefactor, carving scars even as it planted the seeds of life. To picture Earth in this era is to imagine a world under siege, streaks of light ending in fireballs, each one powerful enough to remake the surface. The crust melted and reformed. The skies darkened and glowed. The planet itself seemed locked in an endless battle with the cosmos. Yet within that battle lay the beginnings of oceans, the chemistry of biology, and the chance for stability to emerge. The bombardment was not punishment, it was a stage of growth. Every crater, every molten scar, every fiery shower was part of the process of becoming a planet capable of life. From afar, it may have looked like destruction. In truth, it was creation in disguise, the universe's way of shaping Earth into the cradle it would one day become. Earth's youth, when its surface glowed with magma seas and its skies burned with haze, may seem impossibly distant. Yet even today, the universe offers glimpses of worlds that live as Earth once did. To study these worlds is to look backward in time, as though peering into a cosmic mirror. Two of the most striking examples are our neighboring planet Venus and Jupiter's fiery moon Io, both places where lava still rules, reminders that the universe is far from finished with fire. Venus is often called Earth's twin, and in size and composition, the comparison holds. Both planets are nearly the same diameter, made of similar materials, and formed in the same region of the solar system. But the resemblance ends the moment you set foot, hypothetically, on its surface. Venus is wrapped in an atmosphere of carbon dioxide nearly 100 times thicker than Earth's, with clouds of sulfuric acid that block sunlight and shroud the planet in perpetual gloom. The surface is hot enough to melt lead, a suffocating furnace where even rocks glow with heat. This hellish environment is sustained in part by volcanism. Radar mapping from orbiting spacecraft has revealed vast basalt plains, evidence of ancient lava flows that once swept across the planet. Towering volcanoes, some hundreds of kilometers wide, rise from the surface, their flanks shaped by rivers of molten rock that hardened long ago. Recent studies suggest Venus may not just have a volcanic past, it may still be active. Subtle changes in volcanic vents have been detected, hinting at eruptions in the present day. If true, Venus is not merely a relic of Earth's fiery youth, but a living continuation of it. The planet's surface is, in many ways, frozen in fire. Without plate tectonics to recycle its crust as Earth does, Venus has been resurfaced by massive floods of lava. Entire regions appear smoothed over, as if molten rock had been poured across thousands of kilometers at once. On Earth, lava is usually confined to narrow channels or localized eruptions. On Venus, it has drowned entire landscapes. The result is a world that feels both young and ancient, reshaped in bursts of geological activity, yet locked in a perpetual state of stifling heat. In this way, Venus offers a glimpse of what Earth might have become had its path shifted slightly, a little closer to the Sun, a little more greenhouse trapping, and our planet too could have been a furnace wrapped in haze. Venus is a cautionary reflection, a vision of Earth if it had failed to cool and balance its climate. While Venus offers a large-scale echo of Earth's fiery beginnings, Io provides a more immediate spectacle. This small moon of Jupiter is the most volcanically active body in the solar system. Unlike Earth, where volcanoes are scattered and intermittent, Io's surface is in a near-constant state of eruption. Dozens of active volcanoes dot the moon, some sending fountains of lava hundreds of kilometers high, while rivers of molten rock spread across plains visible from space. Io's fire is not fueled primarily by radioactive decay or leftover heat from its formation, as on Earth, but by the relentless pull of Jupiter's gravity. As Io orbits, it is tugged and flexed by Jupiter and its neighboring moons, a process called tidal heating. This constant squeezing generates immense friction inside Io, melting its interior and driving eruptions that endlessly remake its surface. In simple terms, Jupiter kneads Io like dough, and the result is a world that never rests. From afar, Io's surface is a strange mix of beauty and danger, patches of yellow, red, and white mark sulfur compounds scattered across the landscape, while black scars of cooled lava snake across the plains. Enormous volcanic mountains rise above fields of molten stone. Unlike Earth, Io has no oceans, no weather to soften its features, and no tectonic plates to recycle its crust. It is a raw volcanic world, perhaps resembling Earth at its most active, but magnified and frozen in that state. For scientists, Io is a living laboratory, showing what happens when volcanism dominates a world entirely. Its constant eruptions offer a window into processes that shaped Earth in its infancy, how molten surfaces behave, how volcanic gases influence atmospheres, and how heat escapes from restless interiors. Watching Io is like seeing Earth's past play out in real time, with Jupiter looming in the background as an enormous overseer. Together, Venus and Io remind us that fiery worlds are not confined to the past. They exist now, scattered across the solar system, each carrying lessons about Earth's earlier state. Venus shows the fate of a planet that never escaped its greenhouse haze, locked into a furnace where lava once, and perhaps still, flows. Io shows what happens when volcanism becomes all-consuming, a surface that never settles, always reshaped by fire. Beyond our solar system, astronomers have found exoplanets that may themselves be lava worlds, some orbiting so close to their stars that their surfaces must be oceans of molten rock, glowing under skies filled with vaporized minerals. To imagine them is to imagine Earth during its infancy, fiery orbs circling suns, unstable yet full of potential. The universe is dotted with these reminders, as if to reassure us that Earth's fiery youth was not unique, but part of a wider cosmic pattern. There's a strange comfort in this perspective. Our planet's past may seem distant, but it is reflected in the present of other worlds. Venus and Io remind us that fire is not only destructive, it is also creative. Worlds must pass through violence to achieve stability. In the glow of Io's eruptions and the haze of Venus's atmosphere, we see shadows of the Earth that once was. And in those shadows, we find a deeper appreciation for the fragile balance we live within today. The cosmos is full of fire. Planets and moons are born in it, shaped by it, and sometimes consumed by it. Earth has largely moved past its fiery childhood, but the memory lingers, in volcanoes, in basalt plains, and in the slow rumble of tectonic plates. Venus and Io are the siblings that never left that stage, each locked in its own fiery rhythm. To reflect on them is to remember that our world too was once ablaze, a glowing ember in the dark of space, waiting to cool, to change, and eventually to give rise to life. Earth did not remain a molten world forever. Even in the midst of fire, the planet was slowly losing its heat to the great cold of space. Radiation carried energy outward, a steady glow seeping from the magma ocean into the void. Though the surface blazed at over 1,000 degrees, space was near absolute zero, an infinite reservoir drawing away Earth's warmth day after day, year after year. Gradually, the furnace began to cool. This cooling was neither uniform nor simple. The planet's interior stayed hot for a very long time, and still does today, but the surface was the first to change. As heat radiated outward, thin skins of solid rock began to appear on the molten seas. These early crusts were fragile and short-lived, breaking apart under the stress of convection currents or shattering when new impacts tore across the surface. Yet each time the crust reformed, it grew a little thicker, a little more stable. Piece by piece, the fiery skin of Earth was turning to stone. It's a process much like soup cooling in a pot. At first, bubbles burst and the surface refuses to stay calm. But leave it long enough, and a thin film begins to form, floating on top of the liquid. On Earth, that film was the earliest crust, basaltic rock hardened from molten lava. It was not yet the granite-rich continents of today, but it was a beginning. The formation of this crust changed everything. Where molten rock had once flowed like slow rivers, it now began to freeze into black volcanic plains. Waves of lava still surged from below, cracking and consuming these rocky plates, but for the first time there was something to stand upon, if anyone had been there to try. Though unstable and constantly recycled, this crust marked the transition from a purely molten world to one that carried both fire and stone. Cooling was helped by the gradual decline in bombardments. As fewer asteroids and comets rained from the sky, the surface had longer stretches of time to recover between impacts. Each calm interval allowed new layers of rock to solidify, though collisions still came, reshaping and melting what had already formed. Over time, these intervals of stability lengthened, and the crust thickened with every cycle. Cooling was uneven. Some regions solidified faster, creating larger patches of ground, while others remained seas of lava. These patches drifted and cracked, colliding like rafts on a molten ocean. Sometimes they merged, building larger stretches of rock. Other times, one slab would sink beneath another, pulled down into the still molten mantle. These early stirrings beneath the surface foreshadowed the tectonic activity that would one day define Earth's geology. Above, the atmosphere mirrored the changes below. As the surface lost heat, volcanic outgassing continued, filling the skies with steam, carbon dioxide, and sulfur. But the cooling crust allowed some of these gases, especially steam, to condense. Clouds began to form, heavy with water that would eventually fall as rain. At first, these showers were rare and weak, not yet capable of filling oceans. But for the first time, droplets fell onto rock instead of molten seas, hissing into steam as they touched the hot surface. It was the beginning of water meeting stone, the first step toward rivers and seas. The crust also gave Earth a new texture. Instead of endless glowing magma, the planet now displayed dark basaltic plains, cracked with fissures that glowed where lava still surged through. From orbit, Earth would have looked less like a blazing ember and more like a patchwork of blackened rock veined with fire. The planet's glow dimmed slowly as more of the surface hardened and less molten rock was exposed to space. Yet cooling was never complete. Heat from the interior continued to push upward, breaking through the crust in towering volcanic eruptions. Entire fields of solid rock were drowned beneath new lava flows. Even now, billions of years later, Earth still erupts this way, though today only in scattered places. In its youth, the entire surface was a volcanic plain, constantly remade. Cooling was not a straight march toward stability, but a tug-of-war between heat escaping into space and heat rising anew from the mantle. Over millions of years, this cycle of eruption, cooling, and hardening transformed Earth from a fiery sphere into a planet with a surface that could endure. The presence of a crust altered more than geology, it created a stage for new chemistry. Solid rock exposed to steam and gases triggered reactions that produced minerals impossible to form in pure lava. These minerals, in turn, began shaping the composition of the atmosphere and the oceans yet to come. The crust was not just a physical barrier, it was a chemical frontier where Earth's transformation continued in subtler ways. There is something poetic in fire becoming stone. A planet once defined entirely by molten chaos was learning to cool, to settle, and to hold still. The crust was fragile, yes, but it was proof that stability was possible. Earth was no longer only a furnace, but a world in transition, carrying the memory of its fiery past within layers of black volcanic rock. This cooling process has never truly ended. Even today, Earth sheds heat into space, though far more slowly. The crust we walk upon is thick and stable compared to those early days, but beneath it, the mantle still churns, and at the core, primordial heat from the planet's birth still glows. Every eruption we see now is a reminder of that ancient balance, fire pushing upward while stone holds steady above. To picture Earth in this stage is to imagine a world dimming slowly, its fiery glow fading as the first continents of rock tried to form. The air was still heavy with smoke, the skies still streaked with lightning, but the surface was no longer an endless sea of fire. There were patches of land, unstable though they were, and the planet's face was beginning to look less like a star and more like a world. The cooling of the furnace was not the end of Earth's fiery story, but the beginning of a new chapter. For the first time, there was ground, however fragile, and a delicate balance was forming between the planet's molten heart and the cold of space. That balance set the stage for oceans to gather, skies to clear, and eventually, for life to find a home on stone rather than fire. For millions of years, Earth's skies had been filled with steam, volcanoes breathing it out in endless streams, geysers of vapor rising from the molten mantle, mixing with carbon dioxide, sulfur, and methane to form a dense, choking shroud. The air was hot, the pressure immense, and water could not fall as rain. It lingered as vapor, swirling in heavy clouds that cloaked the fiery planet below. But slowly, as Earth radiated its heat into space, something remarkable began to happen. The atmosphere, though still thick and hostile, cooled just enough for steam to condense. The first raindrops began to form. It's hard to overstate how extraordinary this moment must have been. Imagine a planet that had only ever known fire suddenly tasting water for the first time. Clouds swelled with moisture, heavy and unstable, until they could no longer hold it. Droplets gathered, growing large enough to fall through the dense air. They plunged downward, pulled by gravity, toward a surface that had never before felt their touch. For the first time, rain fell on Earth. The sight would have been surreal, sheets of water tumbling through an atmosphere already heavy with smoke and haze. But the ground was not cool, weathered stone. It was hot, black volcanic crust split by rivers of lava, glowing cracks pulsing with molten fire beneath the surface. When the raindrops struck, they sizzled instantly, vaporizing into plumes of steam. Each drop was erased in a hiss, a fleeting contact between two elemental forces, fire and water. The sound of that first rain would not have been the gentle patter we know today. It was a violent chorus of hissing and crackling. Imagine pouring water onto an iron skillet heated until it glows red, then magnify that sound until it covers an entire planet. The crust shuddered with the sudden contrast, and plumes of steam burst upward, thickening the atmosphere with even more clouds. The cycle repeated endlessly, water falling, vaporizing, and returning to the sky. Yet not all the rain was lost. As the surface cooled, some regions became stable enough for droplets to survive more than an instant. Tiny pools began to collect in cracks and depressions, though they often boiled away quickly. Over time, as the crust thickened and the heat lessened, these pools endured longer. They steamed and bubbled, but they persisted. In the most sheltered places, Earth was beginning to hold water. This was not yet the formation of oceans, but it was the start of a long transition. Each rainfall carried energy away from the atmosphere, cooling it further. Each droplet that struck the ground absorbed heat, releasing steam that rose skyward and spread the cycle wider. From a chemical perspective, these first rains were more than just water falling from the sky. They carried dissolved gases, carbon dioxide, sulfur dioxide, and other compounds, from the atmosphere. When they struck the hot rock, they reacted, leaching minerals and altering the crust's chemistry. These early reactions laid the groundwork for the cycles that would one day regulate Earth's climate. Carbon dioxide, for example, began to be drawn into minerals through weathering. Though the process was slow and often undone by new eruptions, the simple act of rainfall was part of the great planetary laboratory preparing Earth for life. The imagery of this era is striking: black volcanic plains steaming under relentless rain, rivers of lava glowing as they met cascading sheets of water, geysers of vapor rising in response. Lightning storms cracked above, illuminating the spectacle in brilliant flashes. It was not a quiet rain, but a furious one, as if the skies and the surface were at war. Yet in that conflict, a fragile truce was forming, one that would eventually allow the planet to transform from a world of fire into a world of seas. Modern analogies help us imagine this clash. When lava flows into the ocean in Hawaii, enormous clouds of steam billow skyward, punctuated by explosions as water and molten rock violently interact. On early Earth, this was not limited to coastlines, it was everywhere. Every raindrop carried the potential for a miniature explosion. Every lava flow met with hissing and boiling as water fell from above. The entire surface was engaged in this elemental dialogue. In time, the balance began to tip. The crust thickened, eruptions grew less frequent, and the atmosphere cooled enough for rains to persist. Storms gathered and fell in torrents, pouring water faster than it could evaporate. Steam still rose in clouds, but more and more of the water remained behind, pooling in low-lying regions, carving channels, and gathering into vast basins. These were the seeds of the oceans, born from countless raindrops that had first been rejected by fire, but finally found a place to rest. The significance of that first rainfall cannot be overstated. It marked the beginning of Earth's transformation into a world where water would one day dominate the surface. Today, more than 70% of our planet is covered by oceans, and nearly all life depends on water. Yet it all began with vapor cooling enough to fall, droplets hissing as they struck molten stone. There is something deeply poetic in the image of fire and water meeting for the first time. These elements are often seen as opposites: one destroys, the other nourishes. But on the young Earth, their meeting was not simply conflict, it was creation. Fire provided the energy to release gases into the air. Water condensed from those gases, and together they began shaping a planet capable of supporting life. Their struggle did not end either force, it forged a balance. To imagine standing on that early Earth is to picture skies dark with storm clouds, lightning forking across the heavens, and sheets of rain pouring in endless cascades. Beneath your feet, the ground glowed with lava flows, steaming and crackling under the downpour. The air was thick, hot, and heavy with vapor, every breath tasting of minerals and ash. Yet in that storm lay the seeds of calm, the first steps toward oceans, rivers, and the water cycle that would one day sustain forests, animals, and people. Those first raindrops may have seemed small, but they carried the weight of transformation. They were more than water falling from the sky, they were the planet cooling, the atmosphere changing, and the stage being set for oceans to spread and life to begin its improbable journey. Each hissing droplet marked the shift from a world ruled by fire to one balanced between fire and water, a world on its way to becoming the blue planet we know today. At first, the rains hissed into steam as they struck molten stone. But as the crust thickened and the furnace cooled, more and more of that water remained. What had once been vapor hanging heavy in the skies began to pool upon the ground. This was the moment Earth's transformation became undeniable, the moment oceans began to form. The water that gathered on Earth came from more than one source. Much of it was born deep within the planet, locked away in minerals during its violent formation. As volcanoes erupted, they released steam into the air. Each eruption sent clouds of gas into the thick atmosphere, joining the cycle of condensation and rainfall. Slowly, drop by drop, the atmosphere returned what the mantle had given up, and that water began to stay. But volcanic breath was not the only source. From the outer reaches of the solar system came icy messengers, comets and water-rich asteroids, flung inward by the gravitational pull of the giant planets. When these frozen travelers collided with Earth, they shattered, releasing their icy cargo. Each impact was violent, often catastrophic, yet it also delivered precious water to a thirsty world. Between volcanic outgassing and these celestial deliveries, the young planet was being stocked with enough water to cover its surface. As the rains fell harder and longer, low-lying regions of the crust began to fill. The first true bodies of water formed in vast depressions, steaming lakes shimmering in the haze. They boiled and bubbled at first, for the ground was still hot and unstable, but gradually they endured. Streams of runoff carried more water into these basins, and the lakes grew. In time, as rainfall became torrential and unrelenting, these pools merged into something larger. Lakes became seas, seas became oceans, until Earth's face was transformed from fiery plains into a water world. The appearance of the first oceans must have been extraordinary. Imagine standing on one of the early patches of solid crust, looking out over a horizon where the land simply ended in blue. The water stretched into the distance, reflecting the dim light of the sun through a haze of clouds. Steam rose in tendrils from the surface, curling into the air as droplets evaporated, but much of the water remained. For the first time, Earth was wrapped in seas. The sound of these early oceans would have been unfamiliar. Without established winds or shorelines shaped by time, the waves surged unpredictably against the still cooling crust. Steam hissed where water touched volcanic fissures, punctuated by the deep rumble of distant eruptions. It was not yet the calm rhythm of tides lapping a beach, but something rougher, more primal, as the planet adjusted to its new balance between fire and water. The chemistry of these newborn seas was unlike the oceans we know today. Dissolved gases from the atmosphere mixed into the water, creating a brew rich in carbon dioxide, sulfur, and other compounds. The seas were acidic and heavy with minerals leached from the volcanic crust. Yet within this harsh mixture lay the ingredients that would one day foster life. The oceans were not only a physical transformation, but also a chemical stage where molecules mingled and reacted in ways impossible on a dry, fiery world. The sheer volume of water was staggering. Today, Earth's oceans hold over 1 billion trillion liters of water, enough to cover the planet's surface to an average depth of nearly 4 kilometers. In its infancy, the basins may not yet have been that deep, but they grew quickly. Relentless rains, combined with continued delivery from icy impacts, filled the depressions until the surface was dominated by blue. The skies, too, began to change. Where once the atmosphere had been choked with steam and smoke, it now cycled water more efficiently. Clouds thickened, condensed, and poured their rain, but the balance shifted as more water remained on the surface. The greenhouse haze persisted, but gradually the skies cleared enough for sunlight to reflect off the oceans. For the first time, the young Earth gleamed, not as a glowing ember of magma, but as a shimmering, water-wrapped sphere. From space, Earth no longer glowed red and gold with fire, but shone blue, veiled by white clouds. The oceans became mirrors, catching light and scattering it into the darkness of the solar system. To any distant observer, the planet had been remade. The arrival of oceans also brought stability. Water is an extraordinary regulator of heat. It absorbs energy, distributes it, and releases it slowly. With oceans in place, Earth could moderate its temperature more effectively. The violent extremes of heat and cooling softened into gentler rhythms. Though volcanic eruptions still reshaped coastlines and asteroid impacts occasionally boiled regions of sea, the overall balance tilted toward calm. With water came the first cycles that would define Earth for billions of years. Rain fell, collected, evaporated, and rose again into clouds. Minerals dissolved into the seas, settled into sediments, and formed new rocks. Gases exchanged between air and water, shaping the atmosphere. The water cycle, fragile at first, became the heartbeat of the planet, a continuous loop connecting sky, sea, and stone. There is something soothing about picturing these first oceans, despite their strangeness. The surfaces may have been harsh, the chemistry unwelcoming, but the sight of vast blue waters must have brought a sense of calm to a planet long ruled by fire. Waves rolled against rocky shores. Steam curled lazily into the sky. Clouds drifted above, heavy with the promise of more rain. For the first time, Earth had seas, and with them came the potential for life. When we gaze out at the ocean today, we see stability, continuity, and life itself. But every swell, every tide is connected to that first gathering of water billions of years ago. The oceans we know are ancient beyond imagination. Their origins are rooted in fire, steam, and ice. They began as raindrops hissing against lava, as icy comets shattering against the crust, as gases bursting from the mantle into the skies. All that energy, all that chaos, eventually settled into calm blue waters. The arrival of oceans was the single most transformative moment in Earth's history. Fire had built the planet, but water gave it its character. Fire forged the stone, but water shaped the surface, balanced the climate, and prepared the way for life. To close your eyes and imagine those first oceans is to drift into a soothing vision, a planet remade, fire softened by water, chaos tempered by rhythm. Waves lapped against volcanic shores. Clouds rolled gently above. And the air, though still harsh, carried the promise of change. The seas had come, and with them, Earth was no longer only a furnace. It had become a cradle. When Earth's oceans first spread across its surface, they must have seemed boundless. Vast basins of water now covered much of the planet, leaving only scattered fragments of land struggling to stay above the waves. But eventually, through fire, upheaval, and the planet's relentless restlessness, the first islands appeared. They were not lush or green, not havens for birds or trees, but bare and black, their surfaces newly hardened from volcanic fire. These islands were the earliest signs that Earth was beginning to shape geography in a way we might one day recognize. Their emergence was driven by the same forces that had always defined the planet, volcanism and tectonics. Deep within the mantle, heat continued to rise. Magma surged upward through cracks and weaknesses in the crust, breaking through in eruptions that built new land above sea level. The process was relentless. Each eruption spilled lava onto the surface, cooling and hardening into rock. Layer by layer, these flows accumulated until they rose above the waters, forming islands. At first, these islands were small and fragile. Waves battered their edges, breaking down the youngest rocks and carrying fragments back into the sea. New eruptions sometimes destroyed as much as they created, splitting islands apart or drowning them beneath fresh lava. But despite their instability, something new had arrived, the first protrusions of Earth's surface that could truly be called land. Modern volcanic islands offer a glimpse into what this must have looked like. Consider the Hawaiian archipelago, where lava fountains and flows gradually build islands in the middle of the Pacific. Each eruption adds to the land, pushing it higher above the sea. On the early Earth, this process happened on a far greater scale, scattered across oceans that were themselves still forming. These islands would have been stark, steaming, and lifeless, but they represented stability in a world that had long been nothing but fire and water. Over time, volcanic activity concentrated in certain regions, creating clusters of islands. These groups of volcanic peaks were the first hints of proto-continents. Unlike today's continents, with their complex layers of granite, sandstone, and sediment, these early land masses were simple piles of basalt, hardened lava stacked over millennia. Yet they were larger and more enduring than the solitary volcanic peaks that had come before. For the first time, Earth carried patches of land big enough to shape weather patterns, influence ocean currents, and provide a stage for chemical processes that might one day nurture life. The rise of protocontinents was tied to the planet's internal differentiation. Lighter silicic rocks, formed from the repeated melting and recycling of crust, were more buoyant than the denser basalt below. These lighter rocks floated higher on the mantle, creating land that could resist sinking back into the molten depths. The result was the gradual appearance of more substantial land masses, capable of surviving the constant assault of waves and eruptions. The sight of these first protocontinents must have been dramatic. Imagine sailing over the young seas, if such a thing were possible, and seeing jagged peaks rising from the water, their slopes still glowing in places with fresh lava. Steam would billow from cracks where rain met magma, and the air would carry the sharp scent of sulfur and minerals. Though barren and harsh, these islands were important for Earth's developing systems. They provided surfaces for rainfall to collect and run off, carving the first streams and rivulets into solid rock. Minerals leached into the seas, enriching the chemical mix that filled the oceans. Over time, weathering of these rocks would help regulate the atmosphere, drawing down carbon dioxide and contributing to the long-term balance of the climate. Land was more than scenery, it was a key player in the planet's transformation. The oceans, too, were affected by these rising land masses. Waves broke against rocky shores, creating new dynamics in the water cycle. Currents flowed differently, guided by the contours of the protocontinents. Waves pounded cliffs, grinding rock into sand and gravel, which settled into the seabed as the earliest sediments. These processes, subtle at first, were the beginnings of the geological cycles that still shape Earth today. It is tempting to picture these islands as lonely dots in a vast expanse of ocean. And in many ways, they were. But to the young Earth, they represented enormous progress. Only a short time before, the surface had been nothing but fire. Now it was fire and water, and now, at last, stone rising above water. The contrast was striking, a sign that the planet was moving toward greater complexity. These early islands and protocontinents would not last forever. Many were swallowed back into the mantle through subduction or buried under new flows of lava. Others were broken apart by asteroid impacts that still occasionally rained down from space. The surface of Earth remained restless, never allowing land to grow entirely stable. But each cycle of destruction and renewal built up more material, more buoyant rock, and more enduring land masses. Stability, though still far off, was slowly gathering strength. From a cosmic perspective, the appearance of land was significant. A water world without continents behaves very differently from one with them. Continents anchor climates, redirect winds and currents, and provide niches for ecosystems. In their absence, a planet is uniform, its surface smooth and featureless. By raising islands above the seas, Earth introduced variety into its face, the first unevenness in what had been a world of monotony. Even in their lifeless state, these protocontinents were striking features. Seen from space, they would have appeared as dark scars upon the shimmering blue of the seas. Clouds would gather around their peaks, drawn by convection as air rose over the land. Lightning storms would cluster there, their crackling fury illuminating the rough outlines of the islands below. The poetic contrast is hard to miss. A planet born in fire had now called forth water, and from that water, fire rose again, solidified into stone. Lava cooled and hardened, standing against the seas, resisting the endless wash of rain and waves. Fire had created water, and water, in turn, was now reshaping fire into land. Earth had begun to find its balance, not yet calm, but no longer defined by chaos alone. When we look at continents today, vast stretches of granite mountains and fertile plains, it can be difficult to imagine them as the descendants of those humble beginnings. Yet every landmass we walk upon can trace its ancestry back to the first islands that broke the surface, to the jagged volcanic peaks steaming under ancient skies. They were the planet's first attempt at permanence, the earliest signs that Earth was capable of building more than molten seas and endless rain. In those islands rising from the fiery sea, the first hints of stable geography appeared. They were not yet continents as we know them, nor were they enduring in the way we think of land today, but they were a promise, the beginning of Earth's face taking shape, of geography written in stone. From the interplay of fire and water, Earth had drawn forth its first land, a fragile but vital foundation for all the wonders still to come. From its very beginning, Earth has been a restless planet. Beneath the crust lies a mantle that never quite sits still, a churning sea of molten rock that pushes upward, breaks through, and spills out onto the surface. Volcanism is the outward expression of that restlessness, the way the planet exhales the heat and gases trapped within its depths. It is no exaggeration to call volcanism Earth's lifeblood. Without it, the planet would not have the atmosphere, the oceans, or even the continents that define it today. When Earth was young, this breathing was constant and fierce. Gases locked within the mantle surged upward with each eruption, bursting into the skies in colossal plumes. Carbon dioxide, sulfur dioxide, water vapor, methane, and nitrogen poured into the air, changing the composition of the atmosphere with every outburst. These gases shaped the world as profoundly as the lava that built mountains. The atmosphere itself is, in large part, the exhalation of a planet. To put it simply, Earth was learning how to breathe fire. It might seem odd to think of volcanoes as part of a breathing process, but in many ways, that is exactly what they are. The mantle acts like the lungs of the planet, drawing in energy from radioactive decay and the lingering heat of formation, then releasing it through eruptions. Each plume of smoke and ash is a planetary exhale, a sign that the planet is alive inside. If Earth had been silent and still, locked under an unbroken crust, it would have remained a suffocating sphere, unable to build an atmosphere or regulate its own temperature. Volcanism is messy, destructive, and noisy, but it is also how Earth finds balance. The gases released through volcanism were not uniform. Water vapor was one of the most abundant, and it played a central role in forming Earth's oceans. Every eruption vented steam into the skies, where it condensed and fell as rain. Without these volcanic exhalations, the seas would never have filled. Alongside the water vapor came carbon dioxide, which built the greenhouse effect that kept Earth from freezing during its early years, when the sun was dimmer than it is today. Nitrogen, too, was carried upward in volcanic breaths, eventually becoming the dominant component of the modern atmosphere. Not all volcanic gases, however, were so beneficial. Sulfur dioxide, for instance, created acrid clouds and acidic rains, while methane added to greenhouse warming in unpredictable ways. Yet even these less friendly gases were vital to shaping the planet's chemistry. They became the raw materials for reactions in the oceans and atmosphere, reactions that would eventually give rise to the conditions in which life could emerge. Every unpleasant belch from Earth's fiery lungs carried the seeds of future possibility. The style of volcanism in those early times was unlike anything we know today. Modern eruptions, though powerful, are scattered and localized. On the young Earth, volcanic activity was nearly everywhere. Entire plains were formed by enormous lava flows, some stretching for hundreds of kilometers. Imagine a world where eruptions on the scale of Iceland's Loki Fissure or India's Deccan Traps were not rare catastrophes, but common events. The skies would have been filled with ash on a regular basis. Sunsets glowed red and gold, not because of weather, but because volcanic haze painted the light. These eruptions were more than surface spectacles, they were the planet's interior working out its balance. Heat trapped inside needed to escape, and volcanic vents were the pressure valves. Without them, Earth might have overheated and remained locked in molten chaos. By venting both heat and gases, volcanoes allowed the crust to harden, the seas to remain stable, and the atmosphere to grow. They were dangerous, yes, but also essential. If survival had been possible, walking along the surface of that world would have been overwhelming. Around you, cones of basaltic rock rose like chimneys, their tips glowing with fountains of lava. Rivers of molten stone flowed down their slopes, hissing violently as they met rainwater or the sea. Above, plumes of ash and gas billowed upward, spreading across the sky. The ground trembled with each eruption, and the air was thick with the hiss of escaping steam. It would have seemed chaotic and terrifying, yet this was simply Earth breathing, exhaling the products of its own interior. Even today, the legacy of this fiery breathing remains. Volcanoes still dot the planet, from the fire belts around the Pacific to the mid-ocean ridges that stretch like scars across the seafloor. They are fewer and more isolated than in the planet's youth, but they remind us that Earth is still alive inside. Every plume of smoke from Stromboli, every eruption from Kilauea, every hiss of steam from Icelandic vents is part of the same process that once filled the skies with fire. Humans often think of volcanoes only in terms of destruction. They bury cities in ash, trigger tsunamis, and disrupt climates. But they are also creators. Volcanic rock builds islands. Fertile soils form on their slopes. Minerals released in eruptions become part of life's building blocks. Even the air we breathe is, in part, the gift of countless eruptions that vented nitrogen and oxygen precursors into the sky. When you take a breath, you are inhaling a mix shaped by the long exhalations of the Earth itself. There is a gentle humor in thinking of Earth as a planet that once coughed, sputtered, and eventually learned to breathe steadily. In its youth, the volcanic lungs were overactive, filling the skies with smoke and flame. Over time, as the planet cooled and stabilized, its breathing slowed, but it never stopped. Earth may not breathe fire as often now, but every so often it reminds us that it still can. The metaphor of breath captures something deeper about volcanism, its role in keeping the planet in motion. Breathing is rhythm, an exchange between inside and outside, a sign of life. Earth's eruptions, too, are rhythmic. They release heat and gases, reshape the crust, and then pause before beginning again. On the grandest scale, they form cycles of activity that span millions of years, bursts of fire followed by quieter periods of calm. These cycles have guided Earth through climate shifts, mass extinctions, and the slow evolution of continents. To reflect on this is to see volcanism not just as a destructive force, but as the pulse of a living planet. Without it, Earth would be lifeless rock, inert and silent. With it, Earth became dynamic, breathing out the air that would one day sustain forests, animals, and people. Volcanism is messy, unpredictable, and sometimes frightening, but it is also the sound of Earth alive, exhaling its history with every plume of smoke. When you watch a volcano erupt today, you are witnessing more than a spectacle. You are watching the ancient breath of the planet, the same breath that once built an atmosphere, filled the oceans, and set the stage for life. Earth may not have lungs, but it does have a voice, and that voice speaks in fire. The first oceans did not begin as clear blue waters stretching peacefully across the globe. They were steaming, mineral-rich cauldrons, restless and turbulent under skies heavy with volcanic clouds. Into these early seas poured the breath of the earth, gases from endless eruptions hissing through fissures in the crust, bubbling upward in plumes of steam. It was here, in the strange chemistry of fire meeting water, that the raw recipe for life was first mixed. Every volcanic eruption carried more than just heat and lava: carbon dioxide, methane, ammonia, hydrogen sulfide, nitrogen, and water vapor rose in vast clouds and dissolved into the oceans below. These compounds mingled with minerals leached from newly cooled rock, creating a broth unlike anything found today. The seas of early Earth were not gentle, placid waters; they were reactive laboratories, fizzing with energy, rich in ingredients, waiting for the right spark. Scientists call this stage prebiotic chemistry, the chemistry that came before biology. It was the period when simple molecules combined into more complex ones, laying the foundation for living systems. In those bubbling oceans, carbon joined with hydrogen, nitrogen, and oxygen in countless combinations, producing amino acids, nucleotides, and other essential building blocks. These molecules are the alphabet of life. And though they are tiny, their formation marked the turning point between a barren planet and one that would eventually teem with organisms. The energy that powered this chemistry came from many sources. Lightning storms raged constantly above the seas, for volcanic plumes filled the skies with charged particles. Each bolt of lightning split molecules apart, allowing atoms to recombine into new structures. Ultraviolet light from the young sun, unfiltered by an ozone layer that did not yet exist, bathed the oceans in radiant energy, driving further reactions. And beneath the seas, hydrothermal vents gushed superheated water rich in minerals and metals, providing both heat and chemical gradients that fueled even more complex interactions. It is remarkable how much of this early chemistry came from fire. Volcanism not only built the crust and atmosphere, it also supplied the gases that filled the oceans with potential. Sulfur compounds from eruptions may have formed the basis of primitive metabolic pathways. Methane and hydrogen created reducing conditions that made complex chemistry more likely. Even iron released from volcanic rocks played a role, catalyzing reactions that built larger molecules from smaller ones. In a very real sense, Earth's fiery lungs were not only exhaling destruction, they were breathing the seeds of biology. The early seas must have looked strange to modern eyes. Instead of clear waters, they would have been cloudy with minerals, tinted by dissolved iron, sulfur, and other compounds. Some regions may have been deep red from iron oxides, others milky from silicates, still others yellowish from sulfur. Steam rose constantly where hot lava met water, creating foggy horizons. Bubbles fizzed at the surface, carrying gases from the mantle below. To wade into such a sea would not have been refreshing; it would have been like stepping into a bubbling laboratory where chemistry never ceased. One of the most intriguing possibilities is that life's first ingredients assembled in small, sheltered environments along the shores of volcanic islands or near hydrothermal vents. Pools warmed by geothermal heat may have concentrated molecules enough for them to interact. Waves splashing against volcanic cliffs could have created thin films of liquid where reactions occurred more readily. In these microenvironments, chemistry was not random, it was guided by conditions that favored complexity. Over immense spans of time, chance encounters between molecules became patterns, and patterns became the beginnings of order. The famous Miller experiment of the 20th century offered a glimpse into this process. By recreating a simplified version of Earth's early atmosphere and sparking it with electricity, scientists found that amino acids, the building blocks of proteins, could form spontaneously. While the actual conditions of early Earth were more complex than the experiment suggested, the principle remains: with volcanic gases, water, and energy, the chemistry of life can arise naturally. What took place in laboratories in the modern age had already been happening on a global scale billions of years ago. It is tempting to picture these early chemical soups as chaotic, and in many ways, they were. But within the chaos lay pathways of possibility. Certain molecules were more stable than others, more likely to persist and accumulate. these survivors became the foundation for greater complexity. Chains of carbon atoms linked together into organic structures. Rings of molecules assembled, forming the scaffolding for nucleotides and, eventually, the first faint hints of genetic information. Life itself had not yet begun, but the alphabet of biology was being written, letter by letter, in the simmering seas. The role of fire in this story cannot be overstated. Without volcanism, the oceans would have been little more than distilled water, lifeless and inert. It was the gases vented from Earth's interior that enriched the seas with chemistry. Fire turned stone into minerals, minerals into solutions, and solutions into the stage where biology could appear. Earth was not only cooling, it was cooking, stirring a recipe whose outcome would change the planet forever. And what an extraordinary recipe it was: water, gases, minerals, heat, and energy, all combining in countless ways. Most combinations were fleeting, but enough endured to build complexity. The seas became not just passive pools, but active cauldrons, surfaces steaming, depths alive with reactions. If the planet itself was a kitchen, volcanoes were both the stove and the spice rack, providing the heat and the flavor that made the mix interesting. To imagine this chemistry unfolding is to see Earth at its most creative. The skies flashed with lightning. The oceans bubbled with gases. The crust hissed with vents. Every environment offered a new possibility: shallow pools, deep trenches, volcanic shores, each one an experiment running simultaneously in the grand laboratory of the planet. Most of these experiments led nowhere, molecules breaking apart as quickly as they formed. But some pathways persisted, refining themselves until, eventually, they crossed the line between chemistry and biology. The fiery breath of volcanoes had filled the seas with carbon, nitrogen, and sulfur. Cooling rains had provided water in abundance. Lightning and sunlight had supplied energy. All the necessary pieces were in place, waiting for the improbable leap that would turn chemistry into living cells. It is humbling to consider how central fire was to this process. We often think of volcanoes as destructive, yet without them there would have been no air to breathe, no oceans to drink, and no chemistry to give rise to life. The same eruptions that blackened the skies also enriched the seas. The same fiery plumes that belched poison also delivered possibility. Fire, far from being an enemy of life, was one of its first allies. In the cauldron of early Earth, chemistry was destiny. Volcanic gases mixed with oceans, minerals dissolved and recombined, and energy sparked new arrangements. From these humble beginnings came the first whispers of biology. Fire had built the planet. Water had softened it. Together, they stirred the pot of creation. The seas were no longer only seas, they were laboratories, simmering with the ingredients of life. And though the recipe would take millions of years to finish, the first steps had already been taken in the bubbling, steaming, fire-fed cauldrons of a young and restless Earth. For countless ages after its fiery birth, Earth's skies were cloaked in haze, thick with volcanic gases, ash, and steam. They glowed red and orange, streaked with the smoke of eruptions, and darkened by the dust of impacts. The sun, when it appeared at all, was a blurred disk behind curtains of cloud. The heavens were not yet blue, not yet calm, but slowly, almost imperceptibly, the atmosphere began to change. And with that change came a sight both new and familiar: the first clear blue sky. The transformation began as Earth continued to cool. Volcanic eruptions still shook the land, but they grew less constant, less overwhelming. The endless storms of ash that once filled the air began to ease, leaving longer stretches of clearer sky between eruptions. Water vapor that had once hung in choking density now condensed into rain, pouring down in sheets and washing dust and ash from the air. With every downpour, the atmosphere grew a little lighter, a little cleaner. As the oceans expanded, they acted as sinks for many of the gases that had thickened the air. Carbon dioxide dissolved into the waters, combining with minerals to form carbonates. Sulfur and other reactive compounds also entered chemical reactions, their concentrations in the sky slowly decreasing. With fewer pollutants scattering and blocking the light, the atmosphere became more transparent. The heavy veil that had hidden the heavens for so long began to lift. The chemistry of the air itself was changing too. Nitrogen, released from volcanoes and less reactive than many other gases, gradually became the dominant component of the atmosphere. Though colorless and invisible, nitrogen provided the stability the skies needed. It allowed sunlight to pass through relatively unimpeded. And as oxygen slowly began to appear, first in trace amounts from photochemical reactions, and much later in greater quantities from primitive life, the atmosphere became even more conducive to clarity. This transformation was not immediate. It unfolded over millions of years, an atmospheric evolution measured in the slow accumulation of cleaner skies. One day, though no one was there to witness it, the haze must have cleared enough for sunlight to scatter properly. Instead of dim, ruddy light filtering through smog, the heavens above shone with a new brilliance. For the first time, Earth's sky appeared blue. The physics behind that color is simple yet profound. Shorter wavelengths of sunlight, such as blue, scatter more easily off gas molecules than longer wavelengths like red. When the air was clogged with thick aerosols and dust, scattering favored reds and oranges. But once the haze thinned and molecules like nitrogen dominated, the shorter blue wavelengths spread across the sky. The world below was bathed in a cooler, calmer light, and the planet finally looked something like the one we know today. Imagine the moment from the surface. For ages, the skies had been oppressive, heavy with smoke, their colors harsh, their light dim. Now, for the first time, there was openness. A dome of soft, endless blue arched overhead, interrupted only by drifting white clouds. The sun no longer flickered faintly through haze, but shone with clarity, its rays glinting off the oceans below. It was not just a change in appearance, but in mood. The world had grown calmer, gentler, more welcoming. That first blue sky marked a turning point, a signal that Earth had moved beyond its most chaotic youth, that the planet was finding balance. Fire and surges still erupted from volcanoes, but they no longer dominated every horizon. Asteroid impacts still came, but less frequently, and their scars were less lasting. The rains that once boiled instantly now lingered, filling seas and lakes instead of vanishing into steam. The planet was transitioning from constant upheaval to something steadier. A blue sky is so ordinary to us now that we take it for granted. But on a young Earth, that blue sky was a profound novelty, the first sign that the planet's violence was softening, that the chaos of fire was giving way to the rhythms of air and water. In that calm expanse of blue was the promise of stability, a promise that life could one day depend upon. Even before oxygen levels rose enough to create the modern, breathable atmosphere, the sight of a blue sky would have made Earth look more familiar than at any previous time. From space, the planet gleamed with oceans and clouds beneath that azure dome. From the surface, the world no longer seemed trapped under a permanent storm, but open to the heavens. Earth was beginning to look less like a strange alien furnace and more like the home it would become. The arrival of the first blue sky also changed the way energy moved through the planet's systems. Sunlight now reached the surface more directly, warming land and water in predictable cycles. The contrast between day and night grew sharper. Clouds once lost in the haze now formed against a backdrop of clear air, their shapes drifting gracefully across the sky. Winds stirred more freely, guided by temperature differences across land and sea. Weather, in the sense we know it, was beginning to emerge. The symbolism of this shift is powerful. Earth had spent its youth hidden behind veils of fire and smoke, its face obscured, its skies smothered. Now, the veil was lifting. The day Earth's sky first turned blue would have been a quiet revolution. For the first time, the planet wasn't just a realm of molten rock and choking haze, it had a ceiling of air and light. No living thing was there to see it, yet it was a preview of the beauty that would one day greet forests, oceans, and people looking up in wonder. That shift was more than chemistry, it was a change in character. The world was still raw and restless, its volcanoes and storms unrelenting, but it had taken a step toward becoming recognizable. It had moved from furnace to home, from a shrouded cauldron to a place open to sunlight. Billions of years of chaos had to pass before the haze could lift, but when it did, the planet revealed a calm that still defines it. The blue above became a kind of signature, the color of a world that had endured fire long enough to cradle life. Far below that new sky, in the lightless depths of the early oceans, the planet's inner heat was still shaping the story. Along deep fractures in the crust, seawater sank into the rock, met the molten mantle, and returned to the surface superheated and heavy with minerals. These upwellings burst into the cold ocean through towering chimneys, hydrothermal vents, where fire and water worked together in one of nature's most extraordinary laboratories. Around these vents, the seafloor was a place of extremes, icy darkness all around, but plumes of water hundreds of degrees hot surging upward, rich with metals, sulfides, and gases. Where the two met, minerals crystallized out, building spires of black and white stone. They looked alien, yet inside them, chemistry was stirring toward biology. The vents offered everything early chemistry needed: heat, chemical gradients, and a constant supply of raw materials. Their porous walls created tiny chambers where molecules could gather instead of drifting apart. In these sheltered spaces, carbon dioxide and hydrogen sulfide reacted to form organic molecules. Over time, these grew more complex: lipids that could form membranes, amino acids that could link into chains. The building blocks of life were assembling. Energy was the key. The sharp contrast between the hot vent water and the cold, oxygen-poor sea created natural power sources. Some of the earliest metabolic cycles may have begun here, simple energy capture systems that would one day evolve into the machinery of cells. Even now, microbes at modern vents use similar chemical reactions, living proof of how life's first steps might have been powered. Picture that ancient seafloor: black smokers sending up dark, mineral-rich clouds, white smokers releasing shimmering plumes, the water around them glittering with particles. There was no sunlight, no forests, no sky, but there was energy, and with it, potential. Fire from below heated the water carried chemistry into places where it could cool, concentrate, and react. Together, they created the balance life needed to begin. When scientists first explored modern vents in the late 20th century, they found entire ecosystems thriving without sunlight: tube worms, clams, crabs, and countless microbes, all living on chemosynthesis instead of photosynthesis. At the base of these communities were bacteria and archaea using sulfur and hydrogen as fuel, echoing the processes that may have sustained life at the very beginning. The discovery proved that life needs only energy, chemistry, and time, not necessarily light or oxygen. In the deep, protected from ultraviolet radiation and surface storms, molecules could assemble and persist. The vents offered both shelter and opportunity. In their warmth, the first cells may have formed, tiny bubbles of membrane enclosing fragile strands of RNA or short chains of protein. They absorbed energy, copied themselves imperfectly, and competed for survival. They were not yet life as we know it, but they carried its spark, the ability to change, to endure, to evolve. It is striking how quietly this turning point came. The rest of the planet was still a volcanic, unstable place, but in the hidden dark, chemistry was becoming biology. Order was emerging from chaos. The line between non-living and living was being crossed, not in a single leap, but in countless small steps. Fire gave the heat, the gases, and the minerals. Water gave the stability, the medium, and the space for reactions to play out. Alone, neither could have created life; together, they made a world capable of nurturing it. Whether life began here or in shallow pools struck by lightning, the recipe was the same: energy, chemistry, and time. The vents remain one of the most elegant examples of that partnership, a constant dance of hot and cold, mineral and sea, chaos and order. There was no magic, no outside intervention, only the patient work of natural forces. The same laws that shape stars and planets shaped the first cells. The planet cooled, breathed, and mixed fire with water until something new appeared. The spark of life was not a single flash, but a slow glow kindled in the deep, fed by vents that exhaled the Earth's breath, carried by waters that spread across the globe, strengthened by the cycles of fire and rain. From that fragile beginning, life spread to fill the seas, the land, and eventually the skies. In the quiet of the deep, the Earth took its first living breath. The chimneys exhaled gases, the waters received them, and in that mingling, something remarkable happened. The spark of life was born, not in sunlight, but in shadow, not in peace, but in turbulence, not in stillness, but in the eternal rhythm of fire and water working together. From that spark, everything we know, and everything we are, would one day follow. The Earth's earliest years were an age of fire, and that fire left its mark. Its memory is written in stone. Ancient rocks, billions of years old, are time capsules from a world we can no longer see. Most of the first crust was recycled into the mantle or shattered by tectonics, but a few relics remain, in Canada, Greenland, South Africa, and Western Australia. These are not just rocks, they are pages from the planet's oldest diary, written in minerals instead of ink. Among the most precious are the zircon crystals of Western Australia. Tiny, nearly indestructible, and more than 4 billion years old, they hold isotopic clues to the conditions in which they formed. Some suggest that liquid water existed surprisingly early, perhaps only a few 100 million years after Earth's birth. Others carry the chemical signature of crust that had already cooled and stabilized. Even in the planet's fiery youth, these crystals are like sparks frozen in time, fragments of Earth's first experiments in becoming solid. The Canadian Shield holds some of the oldest surviving chapters of Earth's history. Its rocks, more than 3 billion years old, are not random layers of stone but a record of the planet's restlessness, magma welling up and cooling, rivers cutting channels, heat deep underground reshaping minerals. In their patterns, geologists read the lingering pulse of the furnace that once defined the world. Every rock is a memory capsule. Basalt, born from lava, recalls the days when molten rivers swept across young landscapes. Granite, crystallized slowly far beneath the surface, speaks of heat held in patience. Sedimentary layers, though younger, preserve the rains that fell on volcanic islands, the rivers that carried ash to the sea, the slow settling of particles over centuries. Even metamorphic rocks, altered by heat and pressure, are like rewritten manuscripts, still carrying traces of their fiery first draft. Inside these stones, isotopes tell the most intimate details. Ratios of oxygen, carbon, and other elements reveal the temperatures at which minerals formed, the chemistry of ancient waters, the gases that once filled the air. A subtle shift in those ratios might mark a sudden cooling after an eruption, or the circulation of seawater through hot crust. Each measurement is a ghost of conditions long gone, proof that Earth's fire left its fingerprints everywhere. The language of geology is quiet but eloquent. A basalt flow frozen midstream tells of a river of fire halted in its tracks. Ripples in sandstone record waves lapping against a volcanic shore. A seam of quartz marks a fracture where hot fluids once surged upward. These are not just marks in stone, they are sentences in the planet's diary, written without words. Even mountains, far younger than the Earth itself, carry the imprint of that fiery youth. Their granite hearts formed from molten rock cooling slowly over eons. Their rise and erosion are driven by tectonic forces, themselves powered by the heat still rising from the planet's interior. Every cliff, canyon, and pebble is connected to that ancient furnace. The ground beneath our feet is not just scenery, it is fire, transformed into form. Volcanoes are the most vivid reminders. When lava erupts today, it hardens into rock nearly identical to that of Earth's earliest crust. Basaltic flows spread across the land, cooling into black stone pocked with gas bubbles. To hold a piece of fresh basalt is to hold an echo of the material that once covered the globe. The continuity is striking, the same processes that shaped the planet 4 billion years ago are still at work. It is remarkable that any of the earliest crust survives at all. Earth is a master recycler, dragging plates into the mantle, erasing scars, remaking itself again and again. Rocks older than 4 billion years are rare survivors, like pages that escaped a burning library. Studying them is to hear faint echoes of a vanished world. Even when the rocks themselves are gone, their influence remains. The mantle's chemistry, the crust structure, the distribution of minerals, all are legacies of that molten youth. The iron in our blood once sank toward the core in those early days. The oxygen we breathe was once locked in minerals, freed slowly over eons. We are, in a sense, living geology, animated matter forged in fire. A rock in your hand is a fragment of time. A smooth pebble worn by water, a jagged shard from a mountain, a crystal glinting in a stream, each holds the history of heat, pressure, and transformation. To a geologist, rocks are storytellers. Some tell short tales of recent eruptions, others stretch back to when the Earth still glowed with molten seas. There is comfort in knowing the planet remembers. The skies have cleared, the seas have calmed, the continents have shifted, but the stones endure. They are the keepers of memory, carrying the record of fire turned to form. The fire of Earth's youth is still with us, hidden in the heart of every rock. To study ancient stones is to look into a mirror of time. They remind us that the planet was once unrecognizable, a world of firestorms and magma oceans, and that from that chaos came stability, oceans, continents, and life. The fire has cooled, but its traces remain etched into the crust. That fire still burns deep below. The mantle churns slowly, and now and then its heat breaks through the surface in a display that recalls the planet's beginnings. Volcanoes are living windows into that past. When lava spills today, it is not just a modern event, it is a memory surfacing, a fragment of the planet's ancient character breaking through. Hawaii offers one such window. The islands sit atop a hot spot where magma rises from deep within. Kilauea, among the most active volcanoes on Earth, has poured rivers of lava for centuries. Its flows creep through forests, swallow villages, and create new land as they cool into black basalt. Watching lava meet the ocean, sending steam into the sky, is to witness the same creative destructive process that once built the first continents. Iceland tells another version of the story. Straddling the mid-Atlantic ridge, it is a place where the mantle's heat is close to the surface. Eruptions there have reshaped the land repeatedly, from the vast Laki flows of the 18th century to the more recent spectacles at Eyjafjallajökull and Fagradalsfjall. In Iceland, fire is both a hazard and a resource, powering homes and shaping landscapes that draw people from around the world. Elsewhere, volcanoes like Etna, Stromboli, and Vesuvius show how people live alongside fire, sometimes threatened, sometimes enriched by it. Volcanic soils are among the most fertile on Earth, sustaining vineyards, orchards, and fields. The same eruptions that destroy can, over time, make the land flourish. Even the seafloor is alive with volcanic creation. At mid-ocean ridges, lava wells up constantly, building new crust and pushing the ocean basins apart. These hidden eruptions account for most of Earth's volcanic activity, raising mountain ranges that stretch for thousands of kilometers beneath the waves. Volcanoes are storytellers too. Their gases, carbon dioxide, sulfur, water vapor, nitrogen, are the same that once built the first atmosphere. Every plume is a reminder that the planet is still breathing, still alive, still carrying the memory of its fiery birth. Volcanoes are paradoxes in motion, destroyers and creators in the same breath. When Mount St. Helens erupted in 1980, it flattened forests, tore away the side of a mountain, and filled the sky with ash. The devastation was immediate. Yet within a few short years, green shoots pierced the ash fields, animals returned, and the landscape began to heal. In its violence, the volcano had cleared the slate, opening space for renewal, a cycle as old as the planet itself, echoing the time when fire prepared the way for water, stone, and life. They are also our most direct connection to the Earth's hidden heart. Acting as pressure valves for the planet's internal engine, volcanoes let molten rock and gases escape from deep within. Without these outlets, heat would build unchecked, perhaps triggering far greater upheavals. Instead, eruptions release that energy in bursts, dangerous, yes, but also part of the planet's natural rhythm. In their own way, volcanoes are artists. They sculpt landscapes with lava flows, etch mountainsides with ash, and leave behind basalt columns, craters, and calderas. Some of the world's most striking places, Crater Lake's deep blue waters, Iceland's black sand beaches, are the work of volcanic fire. Their beauty is inseparable from their violence. To stand in such a place is to stand where destruction has been remade as form. It's easy to forget that beneath our feet lies a world still hot at its core. The mantle churns, the core glows, and volcanoes are its voice. Each eruption is more than a geological event, it is a message from a planet that has never truly left its molten youth. Fire and water, chaos and stability, destruction and renewal, volcanoes embody the balance that defines Earth. When we watch lava glowing in Hawaii, fissures opening in Iceland, or ash clouds rising from Vesuvius, we are not just witnessing danger. We are seeing the continuity of Earth's story, the persistence of the fire that shaped it. That fire still burns quietly in the depths and flares dramatically at the surface. It will outlast us. In their glow, we glimpse our origins, in their rumble, we hear the echoes of a world once entirely molten. Volcanoes are both memory and prophecy, proof that fire is not only a force of destruction but also of creation. The blaze of Earth's birth has dimmed, but it has never gone out. It still breathes. It still shapes. It still reminds us that beneath the calm surface lies the restless heart of a planet born of fire. Long before humans learned to smelt or cut gemstones, Earth was already a master alchemist. The furnace of its youth was not just chaos, it was a workshop, forging the raw materials that would one day build civilizations. In the churning of magma, minerals crystallized, metals separated, and elements found their places. Out of molten fire came the building blocks of the future. It began with planetary differentiation. In its molten state, Earth's heaviest elements, iron and nickel, sank inward to form the dense metallic core. Lighter silicates floated upward to create the mantle and crust. This was more than a sorting by weight, it was the foundation of chemical diversity. Elements that bonded with metal gathered below, while those that preferred silicate rose above. The planet was organizing itself, setting the stage for the minerals and metals to come. As the mantle convected and magma rose, cooling worked its slow magic. Minerals crystallized in sequence, olivine first, with its deep green crystals, followed by pyroxenes, feldspars, and quartz. These were the alphabet of geology, simple in structure but endlessly varied, building the crust layer by layer. Each crystal was a frozen moment of molten history. Volcanism also concentrated metals. Copper, zinc, lead, and gold, scattered through the mantle, were carried upward in magma and deposited near the surface. Hydrothermal fluids, heated by volcanic activity, moved through cracks in the crust, dissolving metals and redepositing them in veins. These glittering seams would one day be mined for tools, coins, and machines, but for eons they were simply the byproducts of Earth's chemistry. Even gemstones owe their origins to this fiery craft. Diamonds formed under immense pressures deep in the mantle, then rode to the surface in explosive kimberlite eruptions. Garnet, spinel, and peridot grew in molten crucibles, later washed into riverbeds or locked in mountain rock. What we now prize as symbols of beauty began as the natural expressions of heat, pressure, and time. One of the planet's most remarkable creations was the banded iron formation. Billions of years ago, as oxygen began to accumulate in the atmosphere, dissolved iron in the oceans reacted and settled to the seafloor in alternating layers of iron-rich minerals and silica. Born from the interplay of volcanic gases, seawater, and emerging life, these deposits became the vast iron ore reserves that now feed our steel industries. The foundations of modern cities were written into stone by ancient volcanic chemistry. Even basalt, plain to the eye, is a quiet masterpiece. Composed of plagioclase, pyroxene, and olivine, it carries calcium, magnesium, and iron. As it weathers, it releases nutrients into soils and seas, fertilizing ecosystems. In this way, volcanic rock has nourished life for billions of years. The food we eat today is, in part, a gift from ancient lava. From a human perspective, minerals and metals are resources. In the planet's story, they are the legacy of its fiery youth. Every copper wire, every gold circuit, every diamond, every steel beam, all began as products of magma, crystallized in a world still finding its balance. Our technology is, quite literally, the continuation of Earth's volcanic tale. It's worth pausing to see the beauty in this transformation. Fire is often cast as a destroyer, and it is, but in Earth's depths, it was also the great creator. By melting and remelting, sorting and crystallizing, it brought diversity from uniformity. It turned simple elements into complex structures, raw chemistry into glittering minerals. Without fire, Earth would be a barren stone. With fire, it became a treasure house. To walk across a volcanic plain is to see this alchemy in action. Every eruption is an experiment, every cooling flow, a new arrangement of crystals. Over billions of years, these experiments have produced the palette of elements and minerals we depend on. Fire was never careless, it was deliberate. And the work continues. New minerals form as lava cools, as vents exhale into the sea, as rocks are buried and transformed under pressure. Earth has not stopped experimenting. It is still the patient artisan, shaping and reshaping its materials. The jewels we wear and the metals we mine are not relics, they are part of an ongoing creation, a cycle that will outlast us. To hold a piece of volcanic rock is to hold more than cooled lava, it is to cradle a fragment of the planet's memory. In its crystals and metallic glints lies the touch of ancient fire, chaos transformed into form. Each shimmer is a reminder that Earth has always been an alchemist, taking the raw elements of the cosmos, hydrogen, carbon, iron, silicon, and, through heat and pressure, forging the materials of mountains, oceans, and life itself. From molten disorder came structure. From fire came stone. From stone came the resources that would one day build civilizations. Seen this way, fire is not only a force to fear, but one to thank. Without it, there would be no continents to stand upon, no metals to shape, no gems to admire, no fertile soils to grow our food. The fire of Earth's birth still burns in its core, still fuels volcanoes, still crafts minerals in the deep. The planet is still at work, still experimenting, still shaping, and as long as it does, the story of Earth the Alchemist continues, written in stone, metal, and crystal. For as long as humans have watched flames dance in the dark or seen rivers of lava spill down mountainsides, they have told stories about fire. To early peoples, it was never just chemistry, it was life, power, danger, and mystery. Fire warmed and cooked, but it also destroyed. Volcanoes enriched the soil, yet buried cities. Across cultures, myths arose to explain this dual nature, casting fire as both the origin of creation and the harbinger of ruin. In Greek legend, fire was the divine gift that set humans apart. Prometheus, defying Zeus, stole it from the gods and carried it to mortals hidden in a fennel stalk. With it came cooking, metallurgy, and the spark of civilization, but also punishment, as Prometheus was chained to a rock to suffer eternally. The tale captures fire's paradox. It elevates humanity even as it threatens to consume it. In Hawaii, Pele, goddess of volcanoes, is both creator and destroyer, raising new islands from the sea with her molten flows, yet engulfing villages in the same breath. In Maori tradition, the demigod Maui obtained fire from the fingernails of the goddess Mahuika, hiding it in certain trees so it could be coaxed out by friction, a myth that preserves both memory and practical skill. Indigenous Australian Dreamtime stories tell of ancestral beings bringing fire to the land, often as a gift earned through struggle, always with a warning to respect its power. The theme repeats worldwide. In Hinduism, Agni is the flame of sacrifice and the blaze of destruction. In Zoroastrianism, fire is purity and truth, kept burning eternally in temples. In Japan, Mount Fuji's eruptions were seen as divine messages. The Romans imagined Vulcans forged beneath volcanoes, crafting weapons for the gods. Norse myth begins and ends with fire, Muspelheim's flames meeting Niflheim's ice to create the first beings, and at Ragnarok, fire sweeping the world clean for renewal. These myths endure because they are rooted in observation. Volcanoes erupt without warning. Lightning ignites forests. Lava destroys and creates in the same moment. Myths gave these forces meaning, wrapping chaos in story. Even now, with science explaining the mechanics, the stories resonate, they speak to our need to understand a world that can be both generous and merciless. Many of these tales mirror real history. Prometheus's theft is, at heart, the story of humans learning to control fire, something our ancestors did over 1 million years ago. Pele's island making reflects the geological truth of Hawaii's volcanic origins. Maui's fire inwood echoes the real technique of friction fire starting. Norse fire and ice recall the interplay of volcanism and glaciers in the north. Beneath the divine characters lies a keen observation of nature. The ambiguity is universal, the flame that cooks can also burn, the volcano that enriches soil can bury it. Myths taught respect for a force that is never entirely tame. That same paradox shapes life today. Dormant volcanoes often host the richest soils on Earth. Ash and weathered lava release minerals that feed crops, vineyards on Etna's slopes, rice terraces in Indonesia, coffee plantations in Central America. Communities return to these slopes because the land rewards them, even knowing the risks. Volcanoes shape culture as much as they shape land. They become symbols, landmarks, and anchors of identity, Fuji in Japanese art, Etna's glow guiding sailors, Pele's presence woven into Hawaiian chants and dances. To live near a volcano is to live with a constant reminder of Earth's power, inspiring reverence alongside caution. And there is the pull of beauty. Volcanic landscapes are among the most striking on the planet: black sand beaches, emerald crater lakes, jagged lava fields, steaming vents. People travel across the world to stand on a caldera's rim, to watch molten rock meet the sea, to feel the heat of the planet rising through the ground. In those moments, we are not just spectators, we are witnesses to the same fire that shaped the world. The danger never truly disappears. History offers stark reminders: Pompeii entombed beneath Vesuvius's ash, Montpelier's fury erasing Saint Pierre, Nevado del Ruiz unleashing lahars that swept away entire towns. Such events are tragedies, yet they underline a truth: living near fire is a choice made knowingly. People weigh the peril against the promise, and many decide the rewards are worth the risk. In this way, volcanoes are a miniature Earth, a constant negotiation between creation and destruction, between threat and sustenance. They show that life often flourishes at the edges, in places where nature's forces are at their most intense. To stand on a volcanic slope is to stand in two timelines at once. Beneath your feet lies rock born in molten rivers, now weathered into fertile soil. Above you, a mountain that may slumber for centuries, or awaken tomorrow. The relationship is never fixed, it is an ongoing conversation between humanity and the planet's fiery heart. Perhaps that is why, despite all our science and technology, we still choose to live in the shadow of fire. It is not only about fertile fields, striking scenery, or inherited tradition. It is about connection, to the planet's deep history, to the forces that shaped it, and to the reminder that creation and destruction are not enemies, but partners in the same story. Long before people walked these slopes, another kind of creation was unfolding. In the sheltered pores of minerals and the labyrinths of vent chimneys, fragile molecules formed. They were easily broken by heat, radiation, or turbulence, yet some endured long enough to interact, to combine, to experiment. A few arrangements proved more stable. Some could store energy. Some could even make crude copies of themselves. This was not life as we know it, no cells, no DNA, no metabolism in the modern sense, but the pattern had begun, matter organizing itself, using energy to maintain that order, and passing it on. Fire provided the stage, the chemistry, and the energy. Water offered the medium, the stability, and the time. Over millions of years, these primitive systems grew more complex. Membranes became sturdier, enclosing and protecting the chemistry within. Molecules that could speed up reactions, the first enzymes, appeared, making survival more efficient. Eventually, the first true cells emerged, tiny, self-contained worlds adrift in the ancient seas. They were simple, but they carried the spark of something extraordinary, the ability to evolve. With each generation, small changes accumulated. Some cells improved at capturing energy from chemical gradients. Others learned to harvest sunlight. Some formed partnerships, trading resources in ways that benefited both. From these beginnings, the tree of life began to branch. The oceans, once purely chemical, now teemed with microscopic pioneers. They left no visible fossils, but their legacy is etched into the chemistry of ancient rocks and the genetic code of every living thing today. The alliance between fire and water had done more than shape the planet's surface, it had created the conditions for life. The same volcanic heat that once melted the crust now sustained deep-sea ecosystems. The same minerals that built mountains now formed the scaffolding of cells. In this way, Earth's first great transformation was complete. It had shifted from a world of stone and flame to a world where chemistry could dream. The molten chaos had cooled into a cradle, and in that cradle, life began to stir. Once life appeared, it began to change the planet in return. Microbes consumed gases, released others, and slowly altered the chemistry of the seas and skies. Oxygen would not dominate the atmosphere for billions of years, but even in those early days, life was already weaving itself into Earth's systems. The cycle had closed, fire built the world, water softened it, life transformed it. Looking back, the fragility of that balance is striking. A slightly different orbit, and Earth might have boiled away like Venus. A thicker crust, and volcanic gases might never have escaped to form an atmosphere. Without steady rainfall, oceans might never have gathered. The conditions that allowed life to take hold were anything but guaranteed. Yet the balance held. Fire, water, and time worked together, and the improbable became real. Life did not emerge in a gentle garden, but in a crucible of storms, eruptions, and impacts. It was tested from the start, forged in extremes. That resilience remains today, written into microbes that thrive in boiling springs, acidic lakes, and deep ocean vents. They carry the memory of the world from which all life emerged, a world where fire had turned fertile. The transformation of Earth is more than geology, it is a lesson in patience. Billions of years of cooling, raining, erupting, and reacting were needed before seas could settle and life could begin. The earth beneath our feet is the product of endless change, sculpted by both violence and calm. To see a blue sky, to walk a shoreline, to breathe oxygen-rich air is to witness the outcome of that transformation. Every breath and every wave is part of the legacy of fire turned to life. Even now, the memory of Earth's fiery youth is close at hand. Volcanoes still pour lava into the sea. Lightning still splits molecules in stormy skies. Hydrothermal vents still bubble in the deep, nurturing ecosystems that echo life's first cradles. The planet still carries its fire, hidden in its core, breathing it out in plumes and eruptions. Fire did not vanish when life began, it became part of life's story. The same forces once seen as hostile were the ones that made life possible. Fire, water, and stone conspired to build not just a planet, but a home. What began as chaos ended in balance. What began as lava became life's cradle. To reflect on this journey is to see Earth as alive, not accidental. The oceans are ancient gifts, filled with the chemistry of fire. The rocks are cooled remnants of molten rivers. The air is the descendant of volcanic breath, refined by life itself. Everything around us carries the memory of that transformation. The story closes in a circle: from fire came stone, from stone came seas, from seas came life. The glowing sphere of magma became the blue planet, cradle to countless living forms. The balance is fragile, yet enduring. Fire still burns. Oceans still flow. Life still thrives. To live on Earth is to dwell within that circle, part of the arc from lava to life. In the end, Earth's fiery youth was not only destruction, but transformation. Fire was the first step in a journey that led to seas, skies, and life itself. The world that once blazed like a star became a home, a place of forests and rivers, of creatures and people, of endless possibility. Fire made this possible. Its legacy endures in every stone, every drop of water, every breath. From lava to life's cradle, Earth's story is one of fragility, resilience, and wonder, a story still unfolding, written in the rocks, the oceans, and in us, the children of a planet born in fire. Those early seas, restless, mineral-laden, became natural laboratories where the ingredients of fire met the stability of water. Here, molecules learned to join, to endure, to copy themselves. Out of this mingling of heat and calm came the first flicker of biology. Once life appeared, it began to reshape the planet in return. Volcanic gases were transformed by microbes into oxygen, slowly altering the atmosphere. Sediments carried by rivers hardened into stone, preserving the record of these changes. Continents rose and drifted, collided and split, creating new landscapes where life could diversify. Through it all, Earth's inner fire never went out. It still burns in the core, still pushes upward through fractures in the crust, still erupts in reminders of the planet's molten youth. The contrast with Venus shows how narrow the margin was. A little closer to the sun, and Earth might have stayed a furnace, its oceans never forming, its skies forever choking. Instead, our planet cooled just enough, balanced itself just enough, to become a cradle. The difference between a home and a wasteland came down to chemistry, distance, and time. That Earth found its balance is both a scientific fact and a quiet wonder. For as long as we've lived with fire, we've both mastered it and feared it. We told of Prometheus stealing flame, of Pele shaping islands, of gods who breathed fire as both gift and punishment. These myths were born from the same awe we feel today, standing near a volcano, watching molten rock redraw the land. They are more than legends, they reflect a truth: fire has always been part of us. It gave us light, warmth, and civilization, just as it once gave Earth its oceans and its air. To live here is to live with that inheritance. The soils that feed us are enriched by volcanic ash. The metals we shape into tools and machines were concentrated by ancient magma. The gemstones we prize formed under the crushing pressures of the deep. Even our own bodies carry fire's legacy, in the iron of our blood, in the oxygen we breathe. Yet it is the gentler face of Earth that defines our daily lives: blue skies, flowing seas, continents draped in forests and rivers. These are fire's gifts, transformed into calm. It's easy to forget that beneath every quiet shore lies a history of firestorms, that beneath every green field is rock once molten. The Earth we know is not separate from its fiery past, it is built upon it. This story is fragile. A small shift in balance could have led elsewhere: too much heat, and the oceans would have boiled away; too little, and the world might have frozen. Yet it is also a story of resilience. Fire, water, and stone endured long enough to make life possible. And life proved strong enough to change the planet in return. Earth's path was never guaranteed, but it was possible. And possibility was enough. There is a quiet symmetry in how the circle closes. From fire came oceans, from oceans came life, and from life came beings capable of asking how it all began. We, the descendants of that transformation, can look back across billions of years and see the arc of a story written in rock and sea. The molten rivers are gone, but their legacy is under our feet, in our breath, and in the questions we ask about our origins. Perhaps the most remarkable gift of Earth's fiery past is not only that it created continents, oceans, and life, but that it created minds able to wonder. Minds that can read history in stone, imagine magma and steaming skies, and see themselves as part of a planet's great unfolding. Fire gave us not just the means to live, but the capacity to reflect on life itself. And so the story settles into its final cadence. From chaos came calm. From fire came water. From stone came life. The earth that once blazed like a star became a cradle, fragile yet enduring, fierce yet nurturing. Its fiery youth gave us oceans, continents, life, and the ability to look back in awe at how a world born of lava became the home we know. That is the gift of fire, not only destruction, but transformation. Not only chaos, but creation. Not only history, but memory, a memory carried in every stone, every wave, every breath. A reminder that we live on a planet born in fire, and taught, with patience and time, how to hold life in its hands.